Testing, testing. Can you hear me okay? Am I not speaking loud enough? Ah, there we go. I just need to speak louder. Oh, yeah, it's being muted. Okay. just one more minute to somebody else joins, we'll start. Thanks for your patience.
You can increase it using from yeah. Better.
Okay. Yeah, it's 2 minutes. Okay, might as well start. Thank you for being here today. We're going to go over semantic searches in Cassandra, how it can be done today with Cassandra 4, and as well as how we can use it in the future with the new versions, utilizing open source Cassandra with the Apache license, free license to use Cassandra. We'll go over the basics of semantic searches, vector databases, vectors, and later we'll have a demo of both the current versions of Cassandra with OpenSearch, without OpenSearch, as well as with the new version coming out with Cassandra 5. So I am Bassam Shaheen, and with me here is Morelu Miranda. We're from NetApp. We're part of the InstaCluster group within NetApp. So we'll start with vector databases. The key here is that they enable AI and NLP applications to process large scales of data. Right? They utilize various types of information encompassing unstructured data, whether it is text documents, rich media, audio files, video files, and also structured data such as geospatial, tables, graphs, and so on and so forth. So we're able to handle these diverse documents in vector databases. Unlike traditional databases, vector databases are capable of high-dimensional data efficiency. They can perform similarity searches, involve similar points in large data sets based on a query vector. Embeddings embeddings are created for words possessing similar meanings and often occurring together with similar context, so there is a relation between them. And these embeddings are vectors created with a high-dimensional space that captures the aspects of the word's meaning. And so we'll be going over a description of what we're going to do and what the benefits or detriments of using existing versions, as well as the demo. So we'll start with Cassandra 4. So in Cassandra 4, you can store vector data in the database, but there is no specific type for vectors. So in essence, if an application wants to access the vectors, we're having to perform a full table scan every time you want to query the data. The problem with that is with data science, the AI and NLP, you're dealing with large sets of data, and the application is going to have to load all the full tables data into memory, and the limitation on memory could be a problem down the line. Also, the performance is not ideal because having to do a full table scan every time you're trying to get this data. So the approach to do this currently in Cassandra 4 is you have a data processor that downloads the data model as well as loads the file that you want to vectorize. The data processor will vectorize the data based on the model and then stores it in Cassandra in a non-vector column, text or something else. The tool to run a query, the data processor will do a full table scan, do the ranking of the matches, and then present it to the customer. All the workload of the ranking is being done on the application, and therefore it's too burdensome and may have issues with memory and performance. So today with Cassandra 4, we have another option, is to add yet another great open source tool, which is OpenSearch for indexing of vector data. So OpenSearch has a plugin that allows for nearest neighbor searches of your data, as well as being able to store data that will enable us to look up the values from Cassandra and provide the feedback of the query. So the flow here is a bit different than what we saw earlier. So the first step is similar. You have a data processor that's going to go through and pick up the data model and the PDF file. It will vectorize the data, so it will create vectors based on a document ID as well as a paragraph ID. In OpenSearch, the vector data as well as the document ID and paragraph ID are stored. They're in the index. Cassandra will have other data related to the document and the paragraph in Cassandra as metadata. So when from the other side of the equation, you have queries coming against this environment, the data processor will first look at the OpenSearch, run the NLP query against the index, get the vectors that match based on those vectors and not the full data set, just those vectors. Will have the document ID as well as the paragraph ID that can be used to retrieve data from Cassandra. So this will shift the load of doing the matches rankings to OpenSearch. It will reduce the need to do a full scans, so the application is not loaded with too much data. And you have the benefit of having Cassandra with the fast data storage and retrieval. So now I hand it over to Merlo to do a demo of how we're able to show that.
All right, so in this, we will have two demos today. The first one will be the showing what we can achieve with Cassandra 4. Next one, we are going to show an evolution of this. I'm going to do this on a notebook. I preloaded some things here in order to not spend too much time during this demo. But basically, I had to define some functions here to extract text from documents. We are looking for a use case that is, people are looking a lot on this nowadays after that AI hype that we got after ChatGPT. And this is the base of that. So you can have your knowledge base on some folder, for example, or some, I don't know, data lake, whatever, and get your data into a database and be able to look for things there, to information there. This is the part of the pipeline where you can read your data and search for your data. And if you want in the end of the pipeline or in the beginning, you can have an LLM system to do some more complex data management or get information on a different way or a smarter way. Okay, so for the purpose of this demo, we are using fast text model to convert text into embeddings. So in order to do a vector search, you need to have vectors. And this is a pre-trained model that was produced by Facebook research team. And this is free. You can download it and use it. This took like 8 minutes just to load. So that's why I said I preloaded some parts of the notebook. Otherwise, we won't have time here. And the first part of this notebook is we have just functions to get the documents from the folder and index this. So there are functions here to get a PDF file, for example, extract the text, and then convert this into embeddings. Also for PowerPoint files, Word, Excel files as well. So those were the use cases we used and we tried here. We can extend this to other file types. Of course, you need to create functions for that. So those functions, all of those functions are meant for that. And then we have the main function here, which is getting the text after the extraction from the document and converting this into embeddings using this model. 2 notes here on Cassandra 4, we don't have vectors. We don't have a vector data type. So we are going to use a list of floats to store the vectors. All right. And this is a function to insert the data. A simple function like with an insert, we are going to add a file ID we are going to get the file and get chunks of the file, so we are splitting paragraphs. So each paragraph will have a unique ID as well. Then we are going to store the file name, the embeddings that we created with the fast text, the clear text related to that embedding, and then the date that it was created. All right, so in this part, we're passing file path. This is a Cassandra best practice document. We are going to call the function to extract the text from the PDF, convert it into a list of paragraphs with embeddings, and the structure of this list is here, a little bit up. Okay, so each item of this list will have the file ID, the paragraph ID, file name, path, text of the declared text of the paragraph, page number. In PDFs, this makes sense. On Excel, this is going to store the name of the sheet, and the embeddings. All right. Having this list, we can call the function to insert in Cassandra, the function I just showed here on the top. For that file, we produced 302 paragraphs. We set everything in Cassandra, and then we get the part where we need to search. And here is the main problem when you are just using Cassandra 4 with this approach. We need to load all the table. So we did a full table scan here. As you can see, there is no where. So we are just loading the whole table into memory. We are loading the ID, the paragraph ID, and the embeddings and the text. And afterwards, we are going to use this cosine similarity function, which is available on this Python library. And we are doing the similarity comparison in Python. So the weight of this processing is going to the data processor here. So we need to load everything into memory, and if you have a very huge table, this won't be effective. So this may not be a good idea if you have lots of data. Anyway, this works. And here, for example, if I look for cluster, this is going to, I don't know if the size is good, but you can see this found some sentences with cluster here, clusters. So the main thing with the embeddings is that you are not looking for a single word. This is putting the word into a context and looking for similar words around that. So for example, California and San Jose, this would relate to things and return a text. Of course, the similarity score would be different. If you look for San Jose, for example, and you have a text with San Jose, the rate would be higher than if you find California in the middle of the text. Let me go back here. All right, so this is the way to do that with Cassandra, one of the ways to do that with Cassandra 4 only. So this is still possible. It's not ideal. With smaller data sets, this might work depending on your use case. However, you have another way and a more effective way, like Basan said, which is using Cassandra 4 and OpenSearch. So I'm going to connect to OpenSearch here, and I previously created an index using the KNN vector. This is a plugin, actually, a KNN plugin. And this index is having 3 fields, basically, 3 properties. One is the file ID, another one is the paragraph ID, and then we have the embeddings on a KNN vector type. I need to put the dimension. For this case, the dimension is 300. And having that, we can insert all those embeddings in OpenSearch. As I showed, I just added 3 properties here, which are the IDs to identify, basically to cross the information between Cassandra and OpenSearch. And if I do the same search here, where is this? If I do the same search, like look for a cluster, this is what we are going to have, just IDs and a similarity score. And as I have the rest of the metadata in Cassandra, I can use those unique IDs to go to Cassandra, like you're seeing here, and query for the file ID and paragraph ID, so I can enrich my data based on Cassandra. So I can have the similarity score got from OpenSearch, but I can also have all the other information, all the metadata that is stored in Cassandra. So I have the text, the clear text. I have the file path, so if I want, I can go and grab the file. And from this point on, you can insert an LLM and get your text and provide like a nice answer for the end user. Okay. Yeah, that's it for the first demo. I will give it back to Bassam now.
Thank you. So, right now, Cassandra 4 is what's out and released. So, if you have a need to do NLP or semantic search against Cassandra, it's available. But we recommend that you use a tool like OpenSearch as well to be able to perform this action. The great news is that there's recently released is Cassandra 5, and Cassandra 5 beta version. We're looking at the first quarter of next year for Cassandra 5 to be publicly available for use. And embedded in this new version of Cassandra are some features which will negate the need to use OpenSearch, and you just use the one tool, which is Cassandra 5. I'm just kind of curious, how many people here are currently using Cassandra? Okay. And how many are in the AI, here for the AI portion? Okay, cool, thank you. So then I think this will be useful so you can see how it can be easily done in one place. So the benefits of Cassandra is that now it is able to store vectors. So there's a new data type introduced in Cassandra 5 that is a vector data type. It allows running functions against that column of both cosine, Euclidean, dot product, and several functions. It also uses the approximate nearest neighbor function against the data for searching. So you're getting the similarity searches. And the way that this data is indexed is using the new storage attached index that's being introduced also as part of Cassandra 5. So the flow gets simplified again back without having the OpenSearch in there. So the first step is similar in the sense that we're getting the data model, we're getting the document, running the document through the data model, generating the vectors, then storing both the metadata and the vector data in Cassandra. The vectors is in the vector data type column, which then makes it easier for the data processor at the end to do a search against Cassandra on the vector column and retrieve all the data in the one query. So again, back to you.
Yeah. All right, so we are going to the second demo, and on this second one, Cassandra plays a different role here. So before, Cassandra was merely like a metadata store, and now we can have a more power from Cassandra because we have the vector data type on Cassandra 5. So looking straight to the part, let me just connect to Cassandra 5 here, make sure connection is up. Difference between Cassandra 4 and 5 is this data type here, one of those. So you have a vector data type, this is a float, and then I need to put the dimension of the vector, which is matching with the fast text again. All the other functions are the same. So to extract the data, convert the data into embeddings, and et cetera, this is all the same. Difference here is the vector data type, and then we need to create an SAI index on the column in order to be able to search for similarity. As we are still dealing with not a final version of Cassandra, we are getting this warning saying that ANN is still in preview. All right. The part for inserted data is the same as well as the other demo. Same stuff. And then we have the search part. And this is much simpler than before because we can do everything in Cassandra now. And this is like a sample select query where you can look for a text. So this function receives a text, okay? Convert this into embeddings, which is going to be sent to this function here. This will be an array of floats, like before, or like on the other demo. And this query we'll be using the similarity cosine function. This is a native Cassandra 5 function that is going to return the similarity score of each row. And then we can order the rows by the similarity as well using this syntax. So going straight to the point here, if you want to search again for cluster, for example, we will have from Cassandra the similarity index and all the metadata basically. So we can get to whatever we want here. In this case, I got the text. And this is wrong. This wouldn't be text. It's like the file name. And here's the path of the file. So we could get everything directly from Cassandra. So you don't have the need to like deploy an open search or process everything on your data processor, because Cassandra is able to compare, get a similar text, return it to you, and so you have a repository and also a smart part where you can get the similar data from your database. You can, like, just to show we are not just looking for a cluster, we can look for place, for example, and this is looking for, even if there is no place word there, this is going to look for a similar word in the file. Of course, the similarity score is lower than before, but you still have the list here. All right, so Bassam, I don't know if you want to talk about that now or go to the slide.
Sure. So if I go to this slide, just briefly here. Thank you for the demo. You know, this we're both part of, I mentioned earlier, part of Insta. Is that showing the? We're part of InstaCluster, which is a part of NetApp as well. We are a company that provides managed service for multiple open source projects, including Cassandra, OpenSearch, Kafka, Redis. You're able to deploy clusters within minutes on either the cloud, multiple clouds, or you can deploy it on-prem. For this demo, we were able to use both OpenSearch and Cassandra on our managed platform. Easy to deploy, test, and then when we're done, we can then remove it. So we provide support for all these projects as well. So if you're already deployed it in your environment and you're looking for support, we provide that 24/7 on production systems, as well as consulting for implementations and guidance and reviews. So. And to go back to, so this is what it looks like. Is if you log into the console, you'll see I've deployed Cassandra 4, Cassandra 5, as well as an OpenSearch cluster. To create a cluster is straightforward. Pick the technology you want, and just put in a name for a cluster. Let's go with trying to create a Cassandra cluster. Hit next. You can choose a version of Cassandra you wish to deploy. You have from 3. And 5 right now is alpha is in limited availability, but beta will be available for you to use soon as well. Hit next. Pick the region where you want to deploy in AWS, for example. The node type, you can change that to your needs. Hit next, and within 5 minutes, you'll have a cluster created. You can see the cost upfront of what it takes. So we'll click that off. So really, that's kind of our presentation. I want to open up for any questions you may have about this process. Sure. Go ahead, please.
Oh yeah, so I'm a little bit unclear. Maybe you can clarify. In this 5.0 version, you took all those PDF documents, you vectorized it. You parsed it, and you created the embeddings, and then that was what populated the vector database. But in the first one, in the 4.0, you actually use a large language model, and then what did you do there? Did you take a tokenizer?
No,
what was the difference there?
For both, we use fast text to get the text and convert into vectors, okay?
When you convert that, do you use a tokenizer that belongs to a particular LLM? Or
No, not LLM. I use like a fast text, which is a model, pre-trained model, to convert text into vectors with some meaning, okay? So the main difference is on how Cassandra is storing the data. For Cassandra 4...
Why do you need the model then? If you're only taking text and converting it to embeddings, you don't need a model yet. You don't need multi-layer perceptrons and layers.
You need a model to like...
Because the model requires you to train and then you do inference, right?
Yes, but...
here you're just taking text and then you're just creating embeddings. It's not a model.
Yeah, but in order to do a similarity search, you need to have all the text converted into embeddings on the same way. So that model is a trained model with thousands of words, like it's a very high model.
But
And
is that after the fact, after you've already created embeddings, then when you want to do the search, then you use that trained model?
No. The model is just used to convert the text into embeddings. After that, the model is not useless, because every time you need to search for something, you need to get the text you want to search and convert to embeddings using the same model you use it to insert in the database. Okay? And this is the difference here. So this is the clear text view of the model, clear text in Cassandra 4. So this is what the model is producing. So the text is here. This is the text, and this text was converted into this. Okay? This is a list of floats. In Cassandra 5, as we have a vector data type, this is how the vector looked like in Cassandra. Okay, so this is next.
Understood, yeah.
Yeah.
When you do the conversion, how do you know what the end of all these different tokens are, end of scarf, end of padding, and all that part that you typically do in normal?
So in this case, so it's the data model that does that, finds the similarities between words, takes away for comparisons between whether it has a tick mark or not, creates a vector data. Now that vector data is stored in Cassandra. With Cassandra 4, you are not querying that data to do similarity searches. You're just storing the data. The load comes on the application when you're trying to query the data. Is going to pull the full set of data as well as the vectors. The application will perform the search against the vectors to pull the data that's needed and then present you with the ranking of a matching documents.
Yeah, that's the main difference. The part
Yeah.
of comparing the data for Cassandra 4 should be done on your side. For Cassandra 5, Cassandra does that for you. Okay, so you get rid of that processing part, because Cassandra 5 can do that for you.
Yeah.
And
The
return the list with everything, with the score and etc. ordered. Yeah, exactly.
So as an intermediate step, if you are using Cassandra 4, it cannot move to Cassandra 5, you can then leverage OpenSearch to handle the similarity searches using the indexing with the Canon plugin. Yes?
So I was just wondering, do you consider a little vector databases apart from Cassandra, or was that just the
I mean, there are other vector databases out there where I've kind of been playing around with Cassandra piece of it, so I don't know if maybe you have an answer for that. But.
No, for example, we are using OpenSearch to do to complement Cassandra 4. So OpenSearch is only one of the options you have out there. So the good news is just that Cassandra 5 will have that, and so it's another option we will have, and you don't need to deploy another service and pay for it, because everything is in the same place.
And we like that because you still got the free software that you're using. It's very well known for fast writes and reads. So you're leveraging all the benefit and scalability of Cassandra. So those are all great benefits. And now you have the added benefit of you being able to store and retrieve vector data, as we find that's a very good combination. Okay.
All right.
If no other questions, thank you for coming. Appreciate it. And enjoy the rest of the summer.
Thank you.
Thank you.
No, it's okay. It's better. I need to like.
You've got to, yeah, exactly.
There's like, oh wow, that's loud. Yeah. All of a sudden, everyone hears what I'm.
Testing, testing. Wow, it is very sensitive. Yeah. That's that like that. Yeah, just talk.
Actually, try not to because it'll
Yeah,
boom
it will
that loud.
just. Okay, thank you. Okay. Yeah. Okay.
You're so official.
Yeah.
Do we have someone giving us a countdown too? Like,
Marcus will. No, Reyes. And Dean. Well, we got 3 people.
we need like a 10-minute, I feel like, countdown.
Yeah. Oh, good. Is it good? Did he say yes? Wow, we
I
have
have no
more
idea.
people coming. Thank you. Thank you so much. Yeah. Okay. And I also have clicker if you
Okay.
need, but yeah. Okay. Are we good? Good.
Yes.
We're good to go. Okay, great. Thank you everybody for joining our talk today. And in fact, you have so many choices. And so we are very extra thankful for you having chosen us. And I hope it will be a very productive one for you. Like what we'll be talking about will be helpful in what you're looking for. In the kind of direction of Gen AI, stream processors, all of these things that are happening. So our talk is about build a ChatGPT data pipeline with Rising Wave stream processor and Cassandra vector search. It's a bit of an exploratory kind of talk too. As you know, there isn't any true integration yet, right? And then we may be doing some like building out connectors at some point, but the fact is, having, working with data is actually very, very nice because things are loosely coupled. You can actually make kind of connections to it too. Anyway, so this is us, and is it good? Yeah.
Yes.
Okay, so first of all, this is an agenda, just rundown of what we're going to be talking about and who are we, and then just brief overview, just assuming not everybody already know, or work with Gen AI, ChatGPT, which is kind of so popular these days. And so we just kind of give a brief introduction, overview. Then we'll get into introducing Rising Wave, and then Astra, DB Vector, or actually more like it's powered by Cassandra. So, and then we'll talk about this building a ChatGPT data pipeline, giving an architectural conceptual walkthrough. And that should take up like the next 30 minutes or less now. So, okay, so quick intro of the speakers of us. Let me have Corinne introduce first. Yes,
Hi.
first.
Well,
Yeah.
Can you guys hear an echo? Do you hear us okay? All right. Okay, cool. So I'm Corinne. Let me see what it says on my slide so I can like I'm like, who am I? I don't know. So I'm a consultant. I do developer relations related kind of stuff, community and DevRel type of stuff. My background is actually I used to work in entertainment and music before I worked in tech, which is an interesting transition. And like, yeah, that's it. I don't know if it's that interesting. That's my life story.
Yeah.
I mean, I'm sure it's more interesting than that, but.
Great. Yeah, okay, it's my turn.
Yes, it's your turn.
Okay, it's just that I realized I make sure I turn off mute
See, look
my
at
phone.
how you even have, she even has like her jumping with a sword.
Oh.
You know, like how am I supposed to compete with that?
No.
This is Mary jumping
No.
with a sword.
Okay, so this is a quick slide about me, and rather than talking about it all, I just have pictures to represent. And I'm a senior developer advocate at DataStax. As we all know, DataStax is the primary sponsor of this conference, and thank you so much again for coming. And I'm a passionate advocate, and you see me everywhere.
Everywhere.
So anyway, I really enjoy like outreach to the developer community, especially. I'm also Java champion. Also, I run the Chicago Java users group and other users group in Chicago too. So these are kind of things that I've been doing. And also prior to this, I was doing more actually event streaming, reactive systems at IBM, also advocacy and Java space too. So that's about me. And we'll share with you our contact information towards the end of this slideshow. But my interests are really into streaming, distributed systems, and now moving into AI, machine learning, which I'm embracing now. That's what our company is all about these days. Okay, so, but first of all, as I mentioned too, because it may be new, for everybody, not everybody has worked with Gen AI, ChatGPT. So let me step through it kind of quickly to kind of give an introduction to set the stage. So about the ChatGPT Gen AI, as we all know, it came out, ChatGPT specifically, a year ago in November, right, on November 30th, 2022. That's when it came out. OpenAI published it, released it. And it has taken the world by storm, as we all know. And I think it's because all of the things are kind of more like user like kind of enabled, right? For doing things, you can just kind of bring up your Open ChatGPT console, ask questions, and now, of course, there are a lot more chatbot kind of springing up. All of the companies are also doing same kind of thing. So, but ultimately, too, what I wanted to talk about is that this is all about automation to kind of making our lives easier. And it won't, by no means, it will take away our job. And it's actually going to be, kind of peaking on our creativity to create new ways of solving problems. But always remember, the bot isn't going to take us over. And we'll have more kind of interesting things to do, and make us more creative in creating new opportunities too. So let's just really quickly step through like AI, machine learning, just to get an understanding. And this is like the more popular way of describing, in this diagram of AI is mimicking the intelligence and high level wise, mimicking our intelligence and behavior of human beings. And then if you kind of peel down this onion and you see machine learning. Machine learning is really about us trying to train the computer to learn from the data. So then we don't even have to actively training it. It's basically by data. Then they learn from the data and then keep kind of building up your model. However, it can't go too far without more deeper way of doing things, which kind of address the cognitive level. And now it comes in, the core of the onion is really deep learning. And it brings in, the kind of the neural networks. How our brains actually work. And that's where like all the magic is happening. That's where you can find LLMs that we will be talking quickly about. The natural language processing all comes into that inner core of this onion. And let's just real quickly talk about just what is Gen AI. It's a disruptive field in AI in the sense is that now it can actually take prompts that are spoken, that kind of can be spoken language that essentially is very humanly understandable language as input. These are prompts. So it has the potential way of changing the way we create and consume contents too. And it uses a combination of machine learning as well as deep learning to produce the contents, and it's very kind of disruptive ways, a new way of doing things. Because assuming that a lot of you are engineers, and so am I, was I, right? And we learn, right, when we program, what it used to be is that you need to give input that are very strict. You need to have strict rules of specifying the data type, what kind of parameters, and give all the parameters. It's kind of very not like human kind of friendly. But that's the thing with Gen AI is that you can talk to it like you're talking to another person. And that's what is really kind of disruptive about it, as well as it allows us to do a lot more creative things. Yeah. So before Gen AI was actually predictive AI, that actually deals more with business forecast, weather forecast. Those things they are learning from some past data and then making predictions based on that. And that's kind of still kind of doing things the old way. There isn't as much of this, there's probably not much like human understandable way of talking to the bot. But the thing also is that with predictive AI is that the data will expire after a certain periods of time. If you have weather forecasts for 5 days, after 5 days, the data is gone. It doesn't apply anymore. But generative AI can have a lasting kind of effect too. So, okay, so that's that. And then GPT. So ChatGPT deals more with the chat kind of text kind of involved with that in that sense, right? As input, as prompts. But essentially, too, GPT is it stands for Generative Pre-trained Transformer, GPT. So it essentially takes simple prompts, right, in human language format and as input, and then what it does behind the scenes is a lot of pattern matching in there, and it's called like similarity searches. And then it answers questions for the prompts and produce contents that are creative now, writing an essays, writing our code, and then also like designing our dress and maybe writing, or writing a blog post, things like that is very creative. And now then let's get into NLP too. That's important because it's an interdisciplinary subfield of linguistics of computer science. So the concern is to be able to process natural language data sets, right? So that's what is enabling the LLMs, which I'll talk about in a second. And it's kind of dealing with, figuring out what the language is trying to say and then, do all the work that it needs. And it uses rule-based or probabilistic machine learning type of approaches. So it enables computer to actually learn. The actual learning is happening on this kind of level, NLP. And it's kind of allowing you to draw insights, right, from the documents, for example, some input, not just like strictly A equals A or B equals B. It actually goes beyond and creates some context around it. And now it gets into like LLMs, large language models. There's a type of machine learning model. So these are foundational type of model. But typically, though, it takes a lot of money to produce it because we're dealing with petabytes of data or even bigger, right? Like an unending kind of, set of languages. And
Mike, her mic is out.
Yeah, somehow, yeah. Anyway.
Just scream.
Okay, yeah. Okay,
Mary's being tested on her. Here, you want to talk into my mic?
Okay, no worries. Okay. So essentially, large language models is what we kind of developers mostly work with. We're working with LLMs, and that's where kind of window into all of these magic that's behind the scenes, doing all of the cognitive type of work
I'm
behind
gonna
it.
just give you this
Oh.
mic. Hold it.
Thank you. Okay, thanks. Okay. All right, so, okay, LLMs, that's it. And so this is just some examples of these AI, API frameworks that I think most of you are familiar with, the LangChain, Llama 2, Palm, and Hugging Face, all of these. Okay, so now then, let's kind of get into, I just wanted to point out too that how this, you may be wondering, okay, our title of our talk is data pipeline. So we're kind of concerning with data, like processing data, flowing through different kind of steps, within your processing. So now, like with Corinne, Corinne's working with Rising Wave. So yeah, let's have Corinne introduce, and then,
Sure.
and then we'll talk about this test case. So.
Okay, so I'm going to talk a little bit about Rising Wave. This does assume that you guys know something a little bit about streaming in general, streaming data versus like batch and things like that. So stream processing is a data processing approach that deals with continuously flowing streaming data. So if you're familiar with streaming systems like Kafka or Pulsar or Kinesis, as events happen, you are bringing them into the system. Stream processing basically allows you to run queries and processing and transformations on the data as you're bringing it in before you even store it. So that's like the basic kind of high level thing of what is stream processing. So it gives you the ability to do real-time analysis, transformation, and computation of data as it arrives, right? You really can't get any more real-time than that unless you're predicting what's going to happen in the events before they actually happen, which you can eventually do. But it is basically the data's coming in, you're running queries on it, and then you're storing it kind of on the downside. So this is used to extract valuable insights, detect anomalies, and trigger actions based on the incoming data. Okay, I'm talking really loud. Back it off. That's my whole life. They're like, you are so loud. How about this? Too far? Okay, now I have to I'm just gonna go like this and make it a little bit more exciting for you guys. Types of queries in stream processing. Okay, so the types of queries you can do in stream processing. One is filtering. This involves a selection of specific data from a stream based on predefined conditions. I put examples in here because sometimes it's hard to apply and figure out how you can use these different kind of queries. But an example of this is filtering out log entries that contain errors that are needed for immediate attention. Another one is aggregation. It involves summarizing or reducing the data over a certain time window or key. So an example of that is calculating the average temperature over the last 10 minutes from a sensor stream. Then joining streams. This is personally one of my favorites just because I think it's cool. You can literally do this with dozens of streams. So you can combine data from multiple streams based on common keys and conditions and be able to do processing on those multiple streams. So an example of that is combining user click data with product data to analyze user behavior and continuing types of queries in stream processing. Windowing, these queries group data into fixed time intervals or windows for analysis. An example of that is analyzing the total sales for each hour of the day over a week. That's windowing. Pattern recognition is identifying specific sequences or patterns in the event stream, detecting a series of login failures as a security breach attempt. A lot of anomaly detection and fraud detection kind of things fall under this as well. And then stateful processing maintains state information to analyze data over time, such as tracking user sessions. And the example also is monitoring user behavior and detecting when a user session is idle. Very important. For this specific case, I'm going to talk about one kind of use case example. Oh, sorry, I'm going a little ahead of myself. So what is Rising Wave? I'm like, dude, I don't see the next slide, and I was sure it was the next slide. So Rising Wave is an open source distributed SQL database used for stream processing. So it's designed to reduce the complexity and cost of building real-time applications. So if you tried to do stream processing in the past, it can be quite a large, big build. It's not easy to kind of get started, and Rising Wave is meant to tackle that, just being all SQL based, really easy to get started and use. So essentially what it does is it consumes streaming data, so events as they are happening are being brought into the system. It performs incremental computations when the new data comes in, and then updates the results dynamically. I'll dig into this a little bit more just to make sure it's all clear, but it also has a downstream side. Rising Wave has a storage system. So if you're running transformations and queries on the data as you're streaming it in, you have the ability to store it as well to be able to access that data very quickly. It's built in Rust. I think this is cool. That's why I added it. I was like, it's cool, right? It's very performant, and actually the co-founder of Rising Wave happens to be here. So I'm like, oh my God, lots of pressure. So make sure you guys clap, okay? And it's also SQL-based and Postgres compatible. And this is great because if you know SQL, you can do stream processing. So the learning curve is pretty simple. And it's Postgres compatible. So even the downstream side, if you want to use other types of database, you can do that as well. Another cool thing about Rising Wave is the storage and the computation are separate. So you can scale them out independently of each other as well. And it also offers you the ability to do incremental updates on materialized views. Okay, so just kind of high level. So what is Rising Wave? Basically on the left side of the screen. I'm like, I don't know if we're mirrored the same way, but I guess it is. Otherwise, everything would be backwards for you guys. But so events are happening. These streams are coming in, and you could pull in data from a variety of sources, all listed here. You don't really need me to name them unless you want me to. Kafka, Pulsar, Kinesis, whatever. You have the ability to stream them. And then it gives you the ability to do the real-time ingestion. So as the events are coming in, you're bringing the data in real time. You can join streams, as I kind of mentioned before, which I think is super cool and helpful for these types of use cases to be able to join streams. You can do filtering, aggregations, transformations. You're basically running queries in SQL on your data. And then it has the continually updated and queryable states. And then you have the ability to downstream it into a storage area, message queues, databases, warehouses, and data lakes. Okay, so high-level overview of Rising Wave architecture. If you have questions, you can also, again, the co-founder is right over there. I'm not going to point him out, but he's right there. So the Rising Wave architecture, so it includes these key components. So first, there is a serving layer that basically parses the SQL queries and then performs planning and optimization of query jobs. Then you have a processing layer, which performs all the computation. And then you have a metadata management service, which manages the metadata of different nodes and then coordinates the operations amongst these nodes. And then you have a storage layer that stores and retrieves from object storage like S3. Okay, so example of some Rising Wave use cases. I'm going to try to run through these because I know that there's still a lot that we have to cover. So some examples is streaming ETL, the practice of continuously extracting, transforming, and moving data among different systems as the data comes in. So again, the stream processing thing, the big value of it is everything is in real time. Streams are coming in, you're running these queries and transformations on top of it before you're even storing it. Real-time analytics is the practicing of analyzing the data as it's generated or received rather than after the fact. I also just want to touch on something. There's something like a thing called actionable insights where you can create just basically things for your end users to be able to take action on based on those real-time insights. And that's something that's really, really powerful that I think people need to keep in mind when they're thinking about real-time analytics. A lot of times we think about it for use internally, or we think about dashboards and just everything in real time. But when you have any kind of real-time insights and you're providing that to your end users, that can be really, really valuable. Then you have event-driven application, enables continuous event ingestion and processing, detects complex patterns and correlations with a stream of events. There is honestly a ton of different kinds of use cases. There's actually 2 people here from Rising Wave. There's Ray's over here. He can also talk to you guys if you have questions about use cases. He knows a lot about this. So I took a bunch of screenshots, a couple screenshots off of this documentations page. And it's not the whole thing, so it's kind of cut and chopped up. But if you want to see the whole thing, there will be a QR code to be able to access the slides at the end. You'll be able to go and like look at this. You can also just Google fast Twitter events processing Rising Wave and you'll find it. Thank you. Okay. So this is an example of one of the use cases. This is basically like you're processing Twitter events and Twitter hashtags as they're coming in. So this is like just how you would build it out. So like the first step would be launch the demo cluster. Again, there's a lot of things that are chopped up. I kind of just screenshotted pieces of each section. So if you want to see the whole thing, just go to that link. So you launch the demo cluster. Step 2, you connect Rising Wave to the data streams, whether you're using Kafka or Pulsar or whatever. Multiple data streams if you want. And then you can define a materialized view and then analyze the data. And then you query the results. So if you want to see the whole thing, you can just jump in there. And then I'm going to hand it over to Mary.
Yeah, thank you.
We are
okay.
like running.
Yeah, that's right.
Oh,
No problem.
Yeah,
I
she's got a
it now.
handheld. That's
Yep,
fancy.
no problem.
I'm like this tiny little microphone.
Okay, so now it gets into vector search, right? We're kind of going back to talking about ChatGPT, Gen AI type of scenario. So what is vector database and why is it important, right, in the Gen AI kind of space, right? So essentially, too, vector database is a purpose-built database that serves up vector data type for complex machine learning purposes. And it relies on vector embeddings. You know, what is kind of making it possible is these embeddings. So kind of like a quick explanation is that if you normally, right, we're more probably trained to think about things in single dimension. So we're more used to thinking of data as scalar type of data type, right? But then with Gen AI, we need to figure out the context. So then when we do searches and storing of these data, we're not only storing that value, we're also storing more than that. So that's when data needs to be expressed in different forms. So these are like multi-dimensional data, they're vector data type. So if you are like a math person, you are aware of linear algebra. So think of that, then that's what is making the magic happen, is all of these linear algebra, matrix math, all of these things are making it possible. And then it also helps to do all of these similarity searches behind the scenes. So think of, you know, you have a string of data coming in, you do need to tokenize and break down your string, and then each word came out of that will need to map to some numerical representation. So let's say in a database like Cassandra and Astra too, is that we actually will store the data as vector data type. And if you kind of do a selection, there will be arrays of, an array of floating point numbers in it that are being stored that will represent the string that you're trying to store. So that's the idea. And then these are vector embeddings, and so they get stored. So it becomes very important that you want to select a database that have very fast and very stable, fast kind of storage. So for example, like in our Astra Cassandra database, we have making use of storage attached indexing. That's a very, very, very fast too kind of way of doing things. And also as far as doing searches is concerned, that's also very important when you do queries. So we're using the approximate nearest neighbor kind of technique to kind of do selection too of the data, of querying the data. So essentially too, it's a form of like machine learning, like in that space, right? When we're talking about, this is sort of like providing you with feature store, like a feature engineering type of purpose for a vector database. Okay, just real quickly too, what are vector embeddings being used for? It's not just like for, you can use it outside of the context exactly like Gen AI, but essentially too, it is very good because now you are able to store data in vector type of format. So it's good for doing searches, right? Kind of, you rank all of the results by, how close it is to the query string, for example, that these are called similarity searches. And then there's also clustering, and then recommendations kind of scenario. And say, for example, you're doing like shopping cart, at a shopping site, we want to be able to select some products that are close to what you're looking for, then it helps in doing recommendations, kind of test case or use cases, as well as like anomaly detection, right? That's also kind of good to be used for. Diversity measurements, as well as like text kind of classification for that purpose too. Okay, just a real kind of quick too, for those of you who are math savvy, right? So this is what it looks like, and if you kind of represent your data like in normalized vector kind of format using like a two-dimensional kind of space to describe it, you can now see then all of the words are being represented as vector embeddings, and when you look at the graph, that's what they are kind of place in, in this kind of a space too. So it transformed the text into vector. They are called embeddings. And the thing is right now, with OpenAI, the embeddings are 1,536 dimensions, right? There are certain dimensions to how much it can have. And essentially too, as you can see too, is that the version 3 will have more similar to version 2, or actually V1 is more similar to version 2 than version 3. For example, if you kind of do searches, the results, that's how it's kind of determining how close your result is to what you're trying to search for. So here too, it's just another diagram that explains if you're searching for cat, dog, and house, to some searches. And that's what you can kind of look into the graph to see how close is your result to the search result. So you can use this kind of representation. Okay, and then one more. This one too, just kind of wanted to say this gets a bit kind of deeper and show you all the layers of, the searches too. And so this, I won't kind of get into all of the details here, but just to give you an idea. And also too, it helps in storing to have it like be more efficient too, storing it. And also we also have built-in like algorithms to help with fast retrieval. So using like nearest neighbor type of embedding. So I want to point out JVector, for example, is developed by our founder of the technical co-founder, Jonathan Ellis. So he did the JVector, and that's actually becoming very popular. It's really fast, and it makes use of DiskN, which is a Microsoft algorithms too that he's using for doing super fast kind of searches for vector type of embeddings. So, okay, so that's that. And then just kind of real quick, since I don't have as much time, just wanted to point out, right, you can still kind of go back to using traditional database to do this kind of Gen AI things. But the thing, though, you be aware of that it's just not able to handle the complex data type that's required in Gen AI type of multidimensional data sets, all of these things. And also, too, if you want to do that, it's going to take a long time, essentially. So it's not practical. Also, so just really quick kind of description of a data pipeline. How does it kind of brings data to the vector database, right? So normally, too, you would read data from a source, such as S3 bucket or a website or a Kafka topic. Then you process the data to then extract the text to vectorize it. And then you then split the text into chunks of a given size. And then you compute the vector embeddings for each chunk, and then you write the chunk to the vector database. Then after which you will clean up all of the obsolete data from the vector database. So that's how essentially, when you interact with the vector database, these are the steps that will be needed. Okay, so this actually, we only have 3 minutes left to just kind of give you an idea. It's more like exploring, right? Now, Rising Wave, right? How does it work? And we feel that Rising Wave has this kind of a strength, right, in doing some of these processing. And Corinne looks into this Twitter feed type of example. So let me kind of take a look. But let me also kind of point out, too, for a ChatGPT data pipeline kind of experimentation, we like to look at, this is a diagram that explains, you're working with large language model. We're dealing with the training phase and, essentially generate your LLMs. And LLM as such, is limited, as we all know, is static, even though it deals with a lot of data. But the data could come from a year ago. So what happens in between those kind of things, right? So if you kind of look at it, right, we use prompts to kind of prompt the bot to kind of search for things that we need to look for. So I'm thinking, well, using Rising Wave, for example, an example is using the Twitter feed, you want to search for some tags. They can be done very fast using that example that Corinne shows, with Rising Wave. And then from there, too, we can then kind of massage the data and essentially massage the prompt and then essentially then send it to a chatbot to doing like searches that you need to. So that's kind of like the example we like to be sharing, although we just didn't have time to put it up, and then maybe in the next phase we'll have this project actually up running too. But so essentially, just a high-level description of this data flow of the sample. You have Twitter feed, and then send it to Rising Wave, and or kind of like the feed coming from Kafka, and then basically Rising Wave will extract maybe certain tags that you're looking for, maybe the top selected tags, and then from there we construct the chat prompts. And then we'll send it over to the chatbot, in which we're using Astra database vector or Cassandra to kind of help manage the query and storage of these vector data too. So yeah, so I think we're pretty good in here. But we're done. But this is just another example, just wanting to show you where maybe a vector data type or vector data and database can sit, within like a generative AI like RAG application. It's a retrieval augmented generated application. So essentially, kind of think of it like this thing can help with augmenting your the LLM data. So LLM again is very limited in what it can hold. So, okay, all right, good. All right, so I think it's good.
Good, we're done. So,
Yeah, okay.
yeah, there's T-shirts in the back.
Yeah, that's
too.
right. So wanting to kind of point out to you, if you like some T-shirts, you can
Data
get some.
Stacks T-shirts.
Yeah, Data Stacks, and we have some. Corinne, thank you. Corinne put some T-shirts for us, and also some information about our company. The stickers at the back row. So
I
if
love
you
how
want-
she's giving me credit. She brought the T-shirts over here. I literally just put them on the chair.
Thank you. So yeah, thank you. And then okay, resources, of course. And then if we run out of T-shirts, if you can't find your size, please
Yeah,
visit
there's
our
only
booth.
medium and large.
Yeah, that's right. So please visit our DataStax booth upstairs, and there will be plenty of staff to help you and answer questions. And this slide deck, if you're interested, is here. You can reach using this QR code and short bit.ly link. And then these are resources from DataStax. And also our free usage of Vector, our Astra managed cloud platform, Astra. So this is how you can get to it. And you get $25 US dollar per month for free tier usage. It gets renewed every month too. So you get $300 per year. And it's very good enough for personal projects.
I kept it really simple. Honestly, you could just go to risingwave.com, but you guys are in a fortunate situation where you have like the head of product for Rising Wave right there, and then the CEO of Rising Wave right there. So if you have questions about use cases or anything related to Rising Wave, these are the guys to talk to.
Okay, awesome. Okay, I also have a Twitch stream too. I promise to kind of get back to it in the new year. So this is my Twitch stream. If you want to follow me, I'll be doing more hands-on things on there. And if
You
you
are
want
such
to
a
participate,
hustler.
yeah. If you want to participate too, I invite you to join my stream too. That's how it works for me. So. Okay, so with that, we want to thank you again, and this is our information of how you can get a hold of us, and we invite you to stay in touch with us, and LinkedIn, Twitter, or X, and then I also have a Discord channel, and then Corinne has her own consulting service, so if you need her help, yeah, please reach out to her, yeah, so.
I feel like Mary needs like theme music when she comes out, like you know the I'm a Hustler song.
Okay, but thank you so much again for having stayed with us.
Thank you,
and,
thank
yeah,
you.
Thank you, yeah.
1, 2, 1, 2, 1, 2. Yeah, we will go. Okay, so welcome everyone. It's okay. So welcome everyone. My presentation about how Cassandra 4 gave us to cut the cost, and we will be talking about the money. Everyone wants to save some money to have some pay rise or stuff like that, to not let Bezos left to the space one more time and do, or for example, create next weird movie. So, my name is Robert Strupio. I was on the first Cassandra Summit in 2014. The first Cassandra cluster was also made like that. The first Cassandra production fail, and also success. And I'm Java developer, architect, DBA, DevOps, and finally also the FinOps. So, who is the FinOps? The FinOps is the person who play with the Google Cloud, with the AWS, with Azure, to pay as less as possible. For example, looking for some leftovers, cutting costs on everything what is possible, analyze day by day cost explorer, advice in CUD, saving plans, some reserved, and finally, FinOps should save more than just earn. But it's just general rules. But sometimes it could be different. And FinOps also looking for the different weird correlation, like for example here. And yeah, sometimes it's okay that we are finding something. Sometimes it's like here. Okay. So let's go further. So this presentation will be focused only on AWS because I have 25 minutes and I have to do some on that. I know that everyone wants to go to the lunch to eat something, so I will be speed up and also only talk about the AWS. So it's enough. So I don't have enough time to talk about the Azure or about the GCP for the GCP fans. So Cassandra. So Cassandra could be deployed on-prem, cloud, hybrid. Everyone knows that, and we can also choose a DB database as a service, like the Astra Keyspace or any other, or just self-hosted on the bare metal virtual machine or containers. So we will be focused also on self-hosted Cassandra. So where is the cast on the Cassandra which is self-hosted? So mainly it's inside the compute, so CPUs and memory. On the storage, it could be ephemeral, non-ephemeral. On the network, of course, and some other stuff. And of course, the DBA tools. So CPU and RAM. Why it's so important to go into Cassandra 4 to save some cost of the CPU and memory? So Cassandra 4, of course, as everyone knows, supports Java 11. But why it's so important, Java 11? So what is new in the Java 11? So, too long to read, just Graviton is Java 11 for being full speed. There is an article about that. There is a source on the down of the slides that on the Java 8, the Graviton don't have the full speed. So, if we want to cut the cost, just use Graviton. So it's ARM CPU made by Amazon, and the third generation of Graviton contain the DDR5, the RAM memory. We don't have the issue of NUMA, so non-unified memory access, because it's just one socket. There is no Graviton 3 machine which contain more than one physical CPU. Also, if you want to go with Graviton, just go to the newest Ubuntu version. If we, for example,
Okay, it's Apple or Bezos, I don't know who. So basically, if we go to the Graviton, we should use also the Amazon Linux 2, that's the second edition, or Ubuntu 22 or Ubuntu 2023, something the new OS, because on the old legacy, also for example, the cache are not visible. So if you want to have the full speed of Graviton, we should choose the Cassandra 4 because it's Java 11 plus the newest Linux. And finally, in our company in MIWI, we are switching from old Intel machine to the newest Graviton. And finally, after that, we realized that the Graviton third generation are so fast because it is this DDR5 that we can even cut the number of CPUs and memory divide by 2. And there is the final result of the cost on the AWS cloud. I have to cut the numbers, but we see that we are switching for example, R5D 20X large to, for example, R7G X large, or so on. Okay, so storage. Where we can save some money on the storage size. So basically, on AWS, you have two possibilities. Go with the ephemeral drive, so it's local SSD and NVMe. On non-ephemeral is the EBS, so elastic block storage. If we go to the elastic block storage, of course, we have three different options. It could be the standard drive, so it's a magnetic drive. We could go with GP2 or GP3. Don't use GP2 if someone have GP2 on, for example, for the root volume or something else. Let's move that to GP3 because GP3 is less expensive, it's cheaper, and it's much faster. Or IO2 and IO1 and IO2. So, for example, if we compare the same machine, one is R7G 2X large plus GP3 ephemeral drive, the cost to R7GD, so which the drive 2X large, so it contains the local SSD, the price is lower on the machine without the ephemeral drive. But of course, the ephemeral drive is much faster. So we have the ephemeral, but if we are choosing the faster ephemeral drive, which is a local SSD, we have also some additional costs, the cost of ephemeral risk. So if we stop the instance which contains the ephemeral drive will be loose, and we lose all the data which are inside. So we cannot do any fancy feature like the AMI rollout. We cannot do, for example, the detach and attach this drive to another EC2 machine. We cannot easily scale up and scale down EC2 machine, so we lose a lot of capabilities, which we have when we are using EBS drive. And we cannot easily extend or replace our drive. For example, after making some weird stuff on our tables, for example, remove this one which are not used, we want to save some costs by making our disk drive smaller. But we cannot do that using ephemeral drive. We have to go with the EBS, for example. So what is new in the Cassandra 4? If we go to the Cassandra 4, there is another new fancy feature, which is the compression Z standard. If we have some table which contain a lot of data and it's like sometimes rarely used, we have a lot of disk space used, but the CPUs are not so often in use, we can switch easy the compression from default LZ4 to Z standard. After that, we will cut the disk space like 25%. After cut the disk space 25%, we can switch the EBS drive also to the smaller one, also save some cost. Of course, and we do exactly the same. We deleted and we dropped some tables which are not used. We realized that after some long investigation, and we also switched the compression algorithm from the default LZ4 to Z compression on the rarely used table, and after that we cut our EBS drive cost by 2. So another thing. So there is some parameters read ahead on the Linux side. So when we are reading some data from our EBS drive, we're reading something more and place that in our page cache. So the general recommendation, which was on the Cassandra apache.org in the production recommendation page, said that if we are using SSD, we should go to the 4 kilobytes read ahead. But this is the parameters which should be set for local SSD. If we go with GP2, with GP3 or IO2, these parameters will be removed, when will be replaced from the default 256 into 4 kilobytes, make our cluster so stressed that it will be working 2 times worse. We test that very, very hard. So it's the general recommendation. But when we are using the bare metal machine with the local SSD drive, if we are using EBS drive, this general recommendation is not for us. Just remember about that. Yeah, it's not for us because the EBS drive are, of course, the network disk, and the latency are much bigger. And when we are read ahead something from our disk size, and we are keep that in our OS page cache, and we have very fast DDR5 memory, it has the benefits. Yeah. So network. Where we pay for the network, of course, is the interzone, which is free on the AWS. There is a traffic cross availability zone, and of course, cross the region. Service like S3 also could be for free, but it also depends on our configuration. So for interzone, we are not paying anything. So for some cluster which are not so critical and can even lose all the data, we can place that by topology only on one availability zone. But it's very risky, and it's not the general recommendation to avoid any other availability zone. But it's something which we could consider. But if we are thinking about the traffic, which is the inter-region, we have the possibilities to enable compression. So first one is the traffic between the nodes and the client. Of course, we should use for the very small pieces of data the snappy algorithm, which is by default disabled, for example, in Spring Cassandra data, and the traffic between the nodes. So in Cassandra 4, there is the new feature, which is the non-blocking internode connection. It also uses the NetT, not like previously, which was blocking. So we should compress all the data. If by default, of course, then I don't know why, but now it's working. So maybe I talked too much. By default, of course, the traffic between the nodes in Cassandra, the compression between the nodes in Cassandra is enabled for data centers. But if we have different availability zones and just Cassandra in one region, we are using more often the availability zone per rack. So we pay for this traffic between the racks. So my recommendation is to enable this compression between all the nodes, so between the different availability zone. Of course, we also did that. And after enable the clients to node compression, and after enable to compression between the nodes, we also have some cutting cost after that. So basically, if we are sending some data into S3, like for example, the incremental backups, like for example, the backups or something else from our EC2 machine, we should not pay anything for that. But of course, we could have something which is called, sorry for that. We could have something which called is the NAT gateway. So if we are running out of our VPC to something else like the S3 service, we could serve the network traffic directly to EC2, directly to S3, or via NAT gateway. If we are not setting something what's called of gateway endpoints, if someone don't want to pay a lot of bucks for the using NAT gateway, there is free of charge gateway endpoints. And after that, we are not paying for connection to S3 for our EC2. We see the result of enable this endpoint. So, clients anti-pattern. So, Cassandra 4 have some new capabilities, which name is the virtual tables. And after that, we can easily track the service which is the betas. For example, which use the different protocol version, which use something weird, which make a lot of data transfer, which we want to, for example, avoid. And after that, if we are going to the virtual tables and analyze that, we can also remove some weird stuff. Yeah, I don't have time to talk about that. And finally, achieve some better latency. And for example, there is a miss of these slides, but people are often use the Spring Data Cassandra. And inside the Spring Data Cassandra, it's some critical bug. And it's the critical bug in the GitHub 1213. I think that a lot of people know about that, but it was in the Spring Cassandra Data 4 3.x, and it bugs create the prepare statement for every single queries. So if we, for example, are happy that we are using some fancy feature like Spring Cassandra Data, everything is prepared, is made, every query made prepare statement, but it's not reuse that. It's not binding the new value, but for each particular query, create the new prepare statement. So we know that it made that stress on our prepare statement cache, and also generates additional traffic. So and if we go to the table which was introduced in Cassandra 3.11, not in 4.x, we saw that, for example, for each queries we have the new prepare statement, which of course made a lot of latency issue, and of course also generate the additional traffic, which also made the cost. So my general recommendation is to upgrade Spring Data Cassandra to the newest version to avoid that issue. And for example, if we have something which name is the Vault integration, and for each microservice we are generating the new credentials inside our Cassandra cluster, there is in 4.x very extremely important parameters. So we can set up our out read consistency level and out write consistency level as ever we want. So basically by default in the Cassandra 2, 3, I think that even in the 1, there is the consistency level for rich authentication just 1. So if we have situation like that we have some microservices deployed, for example, Kubernetes on something else, and we have this vault which generates the new credentials, we could have the situation that one node goes down, what is normally in Cassandra, because there is some patch, there is some operation, because maybe someone killed -9 by some incident or something else weird. So any other nodes, which was the coordinator during creating the new credentials, contain some hints. If the nodes will go back, it will be sent back to this node which are down. And of course, if we are asking that node by our microservice to know if some users have the permission, have some credentials, the information about that could be stored in our hints and in the queue of the hints. And if we are asking that particular node which was down, we have some out permission issues. And to avoid that, we have to increase the authentication read consistency level, or to not use any weird service like Vault, which creates in every 5 minutes new accounts and propagate that to all the cluster. Okay, of course, if I want to convince people to go into Cassandra 4, there is also something that's its end of life for 3.x. So if you are looking for the support version during the download, the Cassandra, we just read that the end of life is around the December 2023. So now, if we have the version which is out of support, we could have some non-finance risk, which also costs us money. For example, in the past, there is some major bugs, major vulnerabilities like the JMX RCE, so it's remote code execution, which was of course solved by releasing new version. There is, for example, log4shell, another big major bug. For example, 2023 overflow bugs. If we are stay on the legacy version, which not provide the upgrades, we will have the issue that there is some vulnerabilities which is not fixed. Yeah. So summary to go to the launch. So on the Cassandra 4, choose the Java 11, even if it's possible to use Java 8, and of course the newest OS. Of course, go to the Graviton. Always test all good advice if it's match your cases, because some advice could be, some not. For example, the Z standard. In our cases, on the 90% of tables using Z standard, it's good enough. It's not increase the latency, but cut a lot of disk space. Review from time to time Cost Explorer, if you have access, of course. If CPUs are not free cycle, if CPUs have some free cycle, enable compression, and many other good advice. So, final result of our cutting cost mission. There is a question for the audience. Have anyone want to guess how many % we cut our TCO? So total cost ownership. In how many % we cut our TCO? You can guess. 30%. Okay. Next shot. 60. Next shot. Close. For the one who will shot, I have 1 Bitcoin. Not. 76. Not less. Okay, who said 7? Who said 70? Okay, it was 69. So a lot. So it's a Bitcoin for you on the end of presentation. So finally, we go with Cassandra 4. We switch because we should, because the Cassandra 3 is end of life. I don't think if I have to tell something else why it's worth to go to the version which is under the support, but yeah, it's important. So thank you for attending my presentation, and there is a time for a question. No, only that one. Of course, we did a lot of different scenarios, like going to the table, looking on the table stats, going to for example, the we don't have data though, but going to our monitoring and figure out which table is in use, which generate the latency, when we can switch to the compression, different compression, which table are not in use. There is also one table which contain, if I could remember, 10 terabytes of data which are not in use so often. So we go to the business to talk with them if we can remove this table. And finally, when we have some calculation of our EBS drive and how much it will save us the money, they said, okay, so remove that. Which storage? Okay, so the question was on which storage we are. So we are using EBS GP3. Of course, IO2 is much faster and have more and less the performance very similar to local SSD, but it's so expensive. If I will use the IO2, I think that this presentation will be not the cutting cost in name, but will be some, I don't know, changing the drive, changing the EBS type of drive, because IO2 provision only not the disk space, but also the number of IOPS and the throughput. And if we want to have more IOPS than 100, we have to pay for that. On GP3, by default, we have 3,000 IOPS for free in the free tier. Okay, so our big IOPS requirement, it's if we are monitor. So during the peak, it's in the prime time around 2 p.m. where people start to go on MIUI and write some charts and stuff like that. It was like 2,000 IOPS per machine. So we are still in the free tier. In any time when we will observe some big peak of the users, we can go to AWS console or run the Terraform and increase that. If I could remember, AWS allow us to switch one time per 6 hours to switch the IOPS in any time. Okay, so thanks and have a nice time.
keeping the.
I gotta get a copy of that.
Oh, do you? All right. I guess. Oh, woo, we're live. All right. Did you want to see the deck that I rearranged before? You know what? It'll be a surprise.
We can, yeah, surprise me. That's fine.
Yeah. All right. So we'll just go here. All right. So since it's 2:50, we should probably get moving. If you can find a seat. I know there's tons of people in here. Stand against the wall if you have to. That's fine. I'm doing this for the camera. Yeah. Oh, I'm so sorry. You're going to have to come back later. Yeah, there's no room in the room. Boy, you really pack them in. All right, let's start this whole thing. So we're going to talk about RAG. So introduce yourself, Yi.
Hi, I'm Yi. Before this, before joining Llama Index, I joined Llama Index 5 months ago, I think. Before this, I was working at Apple, working on chatbots. And we started the team about 7-8 years ago. And the thing that was sort of like happened this year is it's only the second time in my life that I went to an event and I'm like, holy crap, every single thing that we've built prior to this is completely obsolete. Right? Like completely obsolete. Like, we built these chatbots for WeChat and Apple Business Chat, and we tried to do a good job, obviously. We had a good team. And if you use them today and you compare it with ChatGPT, you're like, which 6-year-old made this chatbot that you built? Prior to that, I was working in algorithmic finance. LLMs have really changed the game. And so I decided, look, I have to do something different. And so I met Jerry, and I'm like, OK, I'm going to join Llama Index. So here I am today.
And then he met me, and life went downhill.
No,
like, come on, do a talk with me, Yi. Fun story, I actually did a talk with Yi and his wife and their baby. We did a panel, all 4 of us. Not kidding. So those of you who don't know me, my name is Patrick McFadden, Apache Cassandra committer. I wrote a book that no one bought, because apparently everyone just loaded it into ChatGPT. Oh, you're all doing what I expected. Yeah, there's my LinkedIn if you want to connect with me on there. So I'm the guy from the video. I talk about Cassandra all the time, mostly. Now I talk about LLM stuff because that's cool. Yeah, RAG all the way. All right, let's get into it. So this is our safe harbor statement. This is you. And when you hear the word Gen AI, all right, let's breathe together. OK, yeah, because nobody knows what this stuff does. He does a little bit, and he does it all day. But we know that you're probably a little stressed out, feeling a little behind, the imposter complex. And then, of course, we all have a boss, and you met mine yesterday, who's like, oh, we need an AI, right? And all right, just be cool, right? Remember, we're a community of people who figure stuff out. We're all smart engineers. Let's work together. It is a cool thing. It is awesome. You just saw how I fixed my son's homework, so that's cool. I didn't have to build a math test, but we're just gonna work through this, and this is a place where you can ask questions and let's just have a good time together and not stress out. All right, let's start from the beginning. So Yi, you're up.
OK, so yeah, absolutely, totally echo what Patrick just said. Right, literally, I started working with these models January of this year, right? So I guess sort of like a quick show of hands, who here has heard of RAG? OK, all right, we got more than
that's like
average
40,
audience.
That's like 80 hands, maybe 100. Wow, that's a huge crowd.
Yeah, the majority of people. OK, so we'll do a little introduction anyway. So if we go to the next slide, we can. So RAG. OK, so LLMs are great at communicating and reasoning, right? They're not as good at knowing things, especially if it's not been part of their training data, in which case they don't know it. So what does RAG do, and how does that help us with this problem? So if we go to the next one.
Do you want to know what the next slide is?
Sure.
You know what it is.
It's
there
fine.
you go.
Yeah,
Right,
so
right.
what is RAG? Like, retrieval augmented generation. When I joined Llama Index, I saw these 3 words, and I'm like, I don't know what these 3 words mean. I know what retrieval means. I know what augmented means. I know what generation means. But you put them together, what do they mean? It's actually a really simple concept. Okay, it's really, really simple. You have an LLM like ChatGPT. Okay, what you need to do is you need to search for the most relevant information, right? Give that data to ChatGPT, and then you get a better response out of it. That's it, right? It's like, you know, if you're talking to anybody, right? If I'm talking to Patrick, right? I want to give him the most relevant contextual information so that he gives me the best response out. If I give him stuff that's not relevant, then he's not going to give me a very good response, right? So similar way, all you want is you want to give the LM the most useful information. So if we go to the next one, right?
Basics.
So how does RAG work in the most basic way? You have a document, and you split it up, right? So you have a document, maybe you split it up into 10 chunks. Why do we even split the document up into 10 chunks? We can just give the entire document to the LLM. Well, there's a couple reasons. One, it's sometimes the LLM has a limit, right? It's called the context limit. They can't take more than a certain amount of text. Sometimes the LLM says, well, you know, it's going to take me longer to process all of this information. Another important thing, they charge you by the amount of information you send to the LLM. The more information you send to the LLM, the more you get charged. And then on top of that, when you give the LLM irrelevant information, guess what? It gives you back data that's not what you want. So what you do is you take the document, you chunk it up, okay? And then you find the most relevant piece of information, right? How do you find it? Well, you use data stacks, right? You find the most relevant piece of information.
Or me, yeah.
Or,
I'll give you the
Patrick,
right
yeah,
information,
or you know, you just
I
have
thought you were
Patrick.
talking about me, yeah. No, you mean the database, right, yeah.
You use the vector database.
Yeah.
And then you figure out, okay, maybe I want 3 chunks. So that's what we call K. That's the math, it's literally the mathematical terminology, the top K chunks. And then you give that to the database. If you've heard of RAG, if you've used RAG, I'm guessing most of you have already done this. But let's talk a little bit about other variations. So the next thing we want to talk about is the
What's the next thing?
The search engines, right? So every search engine out there that does generative AI is also using RAG. So if you use Google Bard, it's referencing its database of websites, and it's retrieving the most relevant information and then outputting the answer for you, right? So that's why it's like, hey, you know, I'm searching. That's what it's doing. Same thing with Bing, same thing with ChatGPT with browsing. So almost undoubtedly, if you've used any kind of modern LM application, you've probably already used RAG in the background. OK, so next slide, we can try it, right? So I guess this might be a little bit hard to see from the back, but I used ChatGPT with web browsing mode, and I said, what 2022 movie won the Oscar? Right? Good question. It did the web browsing search, and it said, the movie Coda won Best Picture Award at the Oscars in 2022, which is correct. They did. Wonderful news for Apple TV+. And I said, well, what year did Coda come out? And they said, Coda actually came out in 2021, which is also correct. So I said, well, is that a 2022 movie? I literally talking to ChatGPT, is it a 2020 movie? And they said, oh, actually, no. Coda came out in 2021. So I realized it's a mistake, right? And I said, OK, so which 2022 movie won the Oscars, right? It's a question that any of you could look up on the internet. And it said, oh, well, no 2022 released movie won the Best Picture award at the 2022 Oscars. Correct. The award went to Coda, a film released in 2021. So this is everything it's saying here is correct, except for the first answer. And this illustrates an important point of doing RAG. Your output is only going to be as good as the retrieved context input, right? So even with ChatGPT, if you ask it this question, because it's not retrieving the right input, it can't give you the right answer, right? So if we go to the next slide, I think that's...
Do you want to guess? Do you want to bet? Remember, I told you I rearranged
No,
your
no,
deck.
no,
Okay,
next
no, all right, here we
slide.
go.
Okay, yeah, so-
oh, yeah, that's
Garbage in, garbage out. Okay, next slide I think is yours, right? Oh, new to RAG. Okay, so we do have a project. It's called RAGs. It's got like, needs to be updated. Actually, now it's got like 5,000 or 6,000 GitHub stars. What it does is it uses an agent to help you build a simple RAG pipeline so you can actually play around with it and see what RAG does. So highly encourage you to check that out. Okay. Now,
all right. Is it my turn yet?
Yes.
Yes. All right. So we have 20 minutes. I'm keeping track of you. All right. So we're doing pretty good. But what I want to talk about is a quick example application because we're all engineers here. We like to get our hands onto something. We don't want it these theory. And I know that because you don't buy my book. Did I say that already? Yeah, you did. Okay. So yeah, you apparently want to do hands-on, right? So we have a little example app. Oops. Hold on. Why is this slide up again? All right. So we have this. We actually use this in production on Astra. This is our. We use this to answer questions, and it connects with Intercom. It connects with Slack, and it's a pretty basic RAG application, and it's meant to be that. But it uses LlamaIndex on the back, and it uses Astra for the vector, and it uses your own docs. And what's pretty slick is it's all available. You can use it today, and there's the URL. And you want to take a picture of that? I'll wait. Hang on, I'll get in it if you want. All right.
Open source.
Open source, completely open source. You can modify it all you want. But yeah, so I'm going to show you real quick what it looks like. And let's see here. So when you go to the repo itself, we have a Gitpod link. And the Gitpod, if you've never used Gitpod, it's super slick because you can click on it and it'll open up all the code into a little IDE that's on the web. And it works pretty good. Don't expect it to be highly performant, but it is pretty cool how it sets up like a nice little environment for you. You can run a server on it, that sort of thing. Think about like Colab notebooks, how cool those can be. This is more for code, right? The free tier works pretty good with GitHub. I feel like I'm selling Gitpod now. Yeah, but it is really cool, and it's great for like when you're sharing things with colleagues, because you can just put it on your repo and send it out. Okay, so that's Gitpod. There's a couple of things in here that are pretty interesting, and I think, hold on, is this my old one, which I had my exact keys from OpenAI? They got exploited. So Yi and I did a workshop, and I put my OpenAI keys in there. Not 20 minutes later, I started getting traffic on it. Yeah, so those are like the new AWS keys, by the way, y'all. Just get rid of those things as fast as you can. Another pro tip, put a limit on your OpenAI, like put a rate limit. It will stop the Bitcoin miners. So we have it. There's something that I should just show you real quick on how this works. There's in the configuration. This is really cool. You could do that. This is what you could do to like have some value with this project. Here, let me reduce my terminal window. What it'll do is it will take like your doc pages or something like that, an HTML link, and it will go through them. It will do some chunking. We'll go through chunking strategies in a minute. But it does some chunking, and it will break it up and vectorize and create the embeddings, and then it'll make a chatbot around your own docs. We use it internally. We fed it everything. As a matter of fact, Jeff talks to it all the time. Thanks, Jeff, just to give it more information. But really, it's meant so that when you say, hey, I have a problem with a Cassandra operations problem, that it won't tell you how to fix an Oracle database, because that's kind of a ChatGPT thing. It's like, oh, my Oracle database, or my Cassandra database crashed. Oh, well, you should go look at your Oracle config file. And like, that's not what I wanted. But think about what you can do with your own docs, right? Especially if it's internal docs, right? Granted, there's about a bazillion of these out there, but it's a pretty cool little project, and it walks you through a lot. So just wanted to show you how that works. And pretty simply, when you connect with Astra, stay logged in. Like I've had this thing running for a while. Oh God, there's those more hackers in there. Man, what's up? But it's very simple. You don't have to set up a data model. You just put in a key. It'll create it all for you. It literally takes like 5 minutes to set up. So that's the quick rundown. We're not going to go through the code. This is really meant to just show that this exists, how simple it is to set up. Go try it. You can find me when I'm walking around. You can hit me up on Slack. I'm on the ASF Slack. You know how to find me. I know you all do, because I know you all, except for you. I've seen all your videos, though, dude. You're awesome. You didn't think I saw you, did you? But anyway, I'd be happy to help you with any of that. So let's go back to you.
Yeah, and I think Patrick brings a very important point here, which is that, like I was saying, you can build a very basic RAG system fairly easily, but there is no what I like to call God mode RAG. Okay, there is no retrieval augmented generation where you can give it every single document of any type you want, and then it just works. Okay, I mean, people are trying to build it, right? I've seen OpenAI try to build it. I've seen Anthropic try to build it. All of them currently still have limitations. And part of that is because humans are extremely creative, right? We have lots and lots of different documents. We like to write them in lots and lots of different ways. There is no one size fits all. So what I'm really excited about this project that DataStax's open sourced, which all of you should try, is that it really is what they're doing in production, right? So getting from that, hey, I built a cool demo, to this thing actually works and we actually are going to use it for real production use cases, for real users, takes some work. So
it also takes some moxie.
Yeah.
Putting Gen AI apps into production, that's a bit of a leap of faith right now. Remember the original statement where like, hey, this is new, you all should just be okay with yourselves? We run into things like, oh, there's limits on OpenAI that we just hit, or
Exactly.
Or we wound up diming out the server that was doing embeddings. I mean, we're finding new problems that we have to solve as engineers.
Yes, yes, and it's very new and it's very rough on the edges. And don't be surprised if you change your prompt and it works fine, and then you show your demo and it's like, my prompt doesn't work anymore, and why? That happens all the time. On top of that, for RAG, there's a whole set of layered strategies that, once again, we don't have time to go through today, but that would be useful in production. So
you have 13 minutes. You can do this. Trust me, man. You got this.
Don't we have to do Q&A also?
That's the 13. Yeah.
Okay. So one of the things that people have talked about is like chain of thought. So there's different prompting strategies, right? So Gemini just came out today. Gemini released, they said, hey, we did really well on this MMOU benchmark. But then if you look at the asterisk, they said, oh, we actually used this new type of chain of thought with 32 different examples, right? So there's lots of different prompting strategies out there. Chain of thought is one of them. Microsoft yesterday, to sort of like take away the thunder, said, oh, actually, we came up with this other one that it works even better with GPT-4, right? So definitely, this is active area research. A second one that we see a lot of use in production is this class of strategies called small to big. So it's you're embedding a smaller chunk and retrieving a larger chunk around it. So why would you want to do that? Let's give an example, right? So if, let's say, each of your chunks is like a sentence, right, which is actually the smallest chunk size that I would recommend, what's going to happen is you're going to have, like, what is the embedding model doing? It's trying to understand the intention of the sentence, right? So if you have that sentence, then it's going to be a very concentrated intention, right? If you give it a page of text, then the embedding model is not, it's going to be a little bit like sort of, okay, more generic. It doesn't really quite understand what exactly that page of text is saying, right? But if it's a sentence, sentence where you have a subject, verb, object, it understands that, right? So you get a much more concentrated embedding, concentrated intention in the embedding if your chunk size is smaller. But what's the problem with smaller chunk sizes? You may miss other useful contextual information. So to give you an example, like let's say if we said, okay, we're just going to make every sentence its own embedding, we'd say something like, okay, Patrick McFadden is a software engineer. Okay, sentence number one. Sentence number two, he's giving a talk today at the AI Dev Conference. Sentence number two. Sentence number three, it says, Patrick
I invented
McFadden,
Java hash maps. Yeah,
Huh?
I invented Java hash maps.
invented Java hash maps.
Yeah.
Okay, there you go. So you got three sentences. right? Now, let's say the query came in and says, what is Patrick doing today? Okay? Or even better, let's say it's what is Mr. McFadden doing today?
Yeah,
okay?
yeah.
Right?
Very
So,
formal.
What embeddings is it going to match? You know, the answer is in question number 2, right? But most likely it's going to match sentence number 2. But most likely it's going to match sentence number 1 and number 3. Why is that? Because McFadden is a very uncommon word in your entire corpus, right?
I love being an example like this. Keep going. This is
Right?
great.
Like, so because of that, the embedding model is much more going to say, well, your sentence has McFadden, right? Your query sentence has McFadden. These sentence number 1 and sentence number 3 have the word McFadden in it. Sentence number 2 does not have the word McFadden in it. Therefore, I'm going to say your query is more similar to sentence number 1 and sentence number 3. So this is where the small to big type strategies come in, right? Because by saying, OK, well, we got sentence number 1, but let's get some stuff around sentence number 1, right? Let's get some more information around sentence number 1. Or instead of just taking that one sentence, then you can get the actual information, which is in sentence number 2. So small to big, it's very, very commonly used in production. I highly recommend you check it out if you're building a production system. Then we have like sub-question decomposition. This is also something that is very commonly used, which is like you have a sentence, and it can have multiple parts, right? You can be like, you know, what's a good example? We say, hey, what happened at the AI.dev conference and at the Cassandra conference, right? So sentence query decomposition can say, OK, well, we're actually, instead of trying to match this entire sentence against the example, we can say, separate that into the Cassandra conference and the AI.dev conference. So, and then we also have like re-ranking, which is another strategy. It's a little bit more complicated, but basically the idea is when you get the chunks back out, you can then re-rank and choose the most relevant chunks based on seeing the chunks that you've already seen. And then we also have stuff with multimodal, which is people are very excited about. You know, Gemini today came out. We have day 1 support with Gemini. So all of these things are part of Llama Index. Unfortunately, I don't have time to show you the code or examples today, but you can check them out. It's in our documentation. And if you go to the next slide, the most important thing is that this is all part of the open source community, right? So Cassandra's open source, Astra's open source, Llama Index is open source, right? The most important thing is we are working on this together, right? We're actively researching these ideas. And for all of you, the most important thing that we can do is have you contribute, right? Help us. Use your data sets, use your use cases, and help us understand how to do this stuff even better. So
I think that really caps us off, because I bet you, I was thinking, you're right, we should leave a lot of Q&A time, because I bet you, all of you, a lot of this is new, especially this slide right here is like the money, right? Because when I first started doing RAG stuff, I was like, there's one RAG to rule them all, right? No, there's like, and y'all keep adding them. There's like, this is the thing I love about Llama Index, is they just keep adding stuff. Here's a pro tip. If you use a Llama Index library in any project, lock the version. Because I guarantee you the next like minor revision will break something. Because they just keep moving forward. And not a bad thing, right?
We're going to fix that.
Yeah, I know.
We're going to fix that.
But it's fast. It's a fast-moving project, and there's a lot of new things happening. And so, yeah, I think why don't we stop and do a Q&A? Because I think that might be the most helpful. And you've got Yi here. He's been doing this for like months.
Yeah, exactly. Months.
Way more than you.
Months of experience.
Yeah. Yeah. He's way ahead of everybody. Right. Oh, Rahul, you going to start this off? All right, go ahead. What's up, Rahul?
Well, but the comment really quickly, it's like, we're looking for a LLM engineer that has 6 years of experience. It's like, oh, really?
Yeah. Yeah, that's an old Cassandra joke back in the day. It was like, we're looking for Cassandra engineers with 10 years of experience. Never mind.
I want to, again, commend you guys on making a very focused library, and I think that it just contributes to the open source community of like being in an ensemble of projects, and I love the focus. One thing that I look for is this kind of metadata filtering, and like other vector databases have like sparse index plus dense vector kind of mixtures. But like with the Llama Index, you guys are a focused project with like basically two interfaces, like index and query. So there's a lot of stuff that you guys are doing that are like magic, but this metadata filtering is like a way to really shrink that universe of potential stuff that comes back, where you're kind of, you could tag the data when it goes in using the LLM and be able to filter it using an LLM as well. Right? So you guys have that in the roadmap at all?
So good thing you asked, and I would separate that into two things. Do we
get
have
a t-shirt, by
metadata
the way.
filtering? Yes, we do. But the second thing is, to your point, right? So we have like two layers of the API. We have the high-level API, and we have the low-level API. And in our experience, most people right now are using the high-level API, right? So the metadata filtering and some of these more advanced features that I'm talking about today, right? They're part of the lower-level API, and we've really been trying to publicize that. We've really been trying to, we have the series of like, Logan has this web series where he's talking about the low-level API. Jerry has a series about building RAG from scratch, right? All of these really trying to say, hey, like look at the more advanced features. So metadata filtering is actually one of them. Right now, it's not as publicized as we need it to be. So that's one of the things that we need to do also. Community education, absolutely.
That's why you get a t-shirt. Next question. Anybody? Fine. Jeff? Yeah.
Fine, I'll ask my question.
Please do.
Are these patterns that are on this slide, do they build on each other? Are they complementary in some ways, or like alternatives? Or I tried number 1, it didn't work, I'm going to try number 2. Like or is there a hierarchy, like some of them are more advanced?
Absolutely, absolutely. So they absolutely build on top of each other. And generally, the way we see people building these systems in production, right, is trying one and then saying, OK, well, looking at the data and saying, hey, what am I missing, right? So the first thing you can do, even before this, the first thing you can do is there's a slider that says, hey, what is my chunk size? So the first thing you can do is adjust that, right? So you adjust the chunk size. And then you're like, well, my embeddings are kind of all the same, right? It's not really getting the, and then you say, okay, maybe I'm going to do the small to big, right? Or you say, look, I really need more examples because the LM doesn't really understand what I'm doing. So that's where the chain of thought comes in, especially with the chain of thought K-shot. So yeah, they're layered strategies on top of each other. I really wish I had put that in the slide, but OpenAI actually, their solutions engineering team actually had this great slide where they said, look, we got this level of accuracy with just naive RAG. I think it was like something around 50%, right? And then they said, look, by adding on this other strategy, right, we got to this level. And then by adding on this other strategy, we got to this level. And then they said, where we ended up with the customer was at 98%. Okay, I don't necessarily think that every application is going to get to 98%, but that concept of layering on strategies really works. And actually, after we saw that, we said, okay, how many of these do we have in Llama Index? The answer is actually we have all of them. We actually have implemented all of these additional strategies. But you really do need to look at your data and layer on the additional strategies.
Max, we had a question.
Yeah, short question. As I understand this, Llama Index is proposed like an end-to-end solution, and I'm curious about the scalability of this solution. Like, could it scale to millions of the documents, 10 millions of the documents? Or is it high bar?
Yeah, so very, very good question, right? So
We have a volunteer doing load testing.
yeah.
Good job, Max.
So
Good contribution.
So does the Python code scale to millions of documents? Yes. Do the strategies scale to millions of documents? Not yet. We are actively working on this. This is very, very interesting. It's a very hard problem if you think about it, right? Basically, ultimately what you're kind of trying to do is you're trying to replicate Google, right? You're trying to redo the search problem, but even better. And embedding search does help you do that. But there's some other steps along the way that we are actively working on.
Yes.
You mentioned numerical estimates earlier. I was wondering if there's an objective way to estimate the quality of the RAG algorithm.
Absolutely, absolutely. So
I don't know this one either, because we talked about this before. It's like, how do you know that you got a hallucination?
Yeah, so there's,
Yeah.
once again, very, very active area of research and development, right? So what we call evaluations, very, very active. We have some built-in evaluation tools you can use with Llama Index, by no means comprehensive. The rest of the industry is also working on evaluation tools, and there's companies that are working on this also. On top of that, there's this question of, do you have the LLM do all the evaluations? So our evaluations are done with LLMs, but sometimes, you might want to have human evaluation also. So how do you integrate that? So very, very active. We definitely, definitely check out our evals page, about the evaluation strategies we have. But yeah, I mean, like if you have a new idea, definitely send it our way also.
All right, we got room for one more question. Yeah, I'm getting the wrap-up thing. You gonna bring out the hook? Please don't. All right, one more question out there. Oh, no one wants the final word. All right, great. Go to the next talk. Don't hang out in the hallway. No, hang out in the hallway. They're all recorded, so you can just talk all day. It's okay. But thanks a lot, Yi.
Thank you so much for the invite.
And you know what? Here's the thing. He didn't know how I crafted. I totally messed up his deck, and he did an awesome job. So let's give him a hand. You did good, man. Let's play presentation jumble again sometime.
Yeah,
okay, cool.
Happy to. Thank you.
Thanks, everyone. Nailed it.
We can.
We don't want to have it
We can do a. Yeah, I mean this is fine.
on the mic right there.
Yeah. Okay.
Should we start?
Sure.
Welcome everyone. This is zero downtime migrations, or in other words, migrating applications between Cassandra clusters of whatever variety with no downtime. We'll get into the nitty-gritty details of what that actually means in just a little bit. My name's Jeremy Hanna. I've been around in the Cassandra community for a while. I would have made it to the first Cassandra Summit in 2010, but my daughter was born. So worked with Cassandra just back that far, working at DataStax for about 11 years now, but in the Cassandra community for about 13 years, I guess.
Yeah. Hi, everyone. My name is Wei Dan. I've been with Cassandra community and DataStax both for just a little over 10 years now. Yeah.
So we're going to be discussing some technology that some tools. So there's what's called a ZDM proxy, or zero downtime migration proxy, and a set of data migration tools that a number of engineers have worked on. We wanted to just not take all the credit for all of this. We're just the people that are actually here physically present. But the list on the right that you see are a lot of engineers that have put a lot of work into the data migration tooling and been in the trenches doing a lot of these migrations over the last couple of years. And the list on the left are those who are primarily focused on what's called our ZDM proxy, the tool itself to help with the no downtime part, keeping two clusters in sync. And Alice Lotini and Joao Rice, in particular, have done a good share of that work, starting about 3 years ago.
Yeah.
So
I see Stefano is also in the audience.
and same with
Thank
Brett.
you.
Brett somewhere out here too, yeah, in the back. So yeah, we have some if you have any additional questions about certain things. So we'd like to just start off with what does it mean to be a zero downtime migration? How you might define that. Want to do it from the perspective of a user or the application developers, because this is the process of migrating applications from an origin to a target cluster, origin cluster to a target cluster without user awareness or service disruption. So if you're on a banking app, you're on a social site, you're on whatever, you're on like a movie streaming service or a game or something like that, you shouldn't see any blip or have to have some sort of like, by the way, at 3:30 this afternoon, something's happening or whatever. They should have nothing like that. And that's not to say that you might not have rolling restarts of your application servers or something like that, just as you would with something that is like stateless or something that can refresh user connections and things like that. So something might be happening under the covers, and we'll go over what those things are. But from a user's perspective, that's using your app or your website or whatever IoT thing, they should have no awareness of what's going on under the covers, except to say that their service is predictable and performant.
Yeah, so one thing I'd like to call out here is that when we say origin and target, which you will see a lot in the diagrams and in the follow-up in some of those subsequent slides. So origin, hopefully that's self-explanatory. That's basically you're migrating from the origin cluster, and then your target is the data you will be going to. So yeah, just want to make sure that you're clear on the terminology.
So the scenarios and use cases, we originally designed this for migration to DataStax has a managed database called Astra, and it's a managed Cassandra, and people have had Cassandra clusters that they wanted to migrate to that. And so we wanted to create tooling to make that simpler for people, but as kind of like a added side benefit from that is that this can really be done for, and we've used it for a number of other reasons. So for instance, and this builds upon what you already have in your toolbox, right? So if you have a Cassandra cluster, you're trying to say, I want to be able to burst from my on-prem into the cloud because I want to go into this other region, or I have this specific event. You can add a data center in a cloud and have it be the same cluster, and you just kind of burst out to that other area with other application servers. This adds something to that capability because under certain circumstances, you don't want to do that. So like if I'm on-prem and I'm going into a cloud provider, there's kind of some detangling, coupling things that you might have. So like authentication or other things having to do with like user management or infrastructure and networking and things like that, that if you don't necessarily want to couple the two into a single cluster, and having two separate clusters that are decoupled completely gives you a lot more freedom. We'll go into how that works. Or upgrading from an older version of Cassandra to a newer version of Cassandra. If you're on 2.1 today using CQL, you might want to go to 5.0 tomorrow when it gets released in GA, and you've kind of proven it out. And so not having to go through, if you've been in that situation, going through a lot of versions of Cassandra, upgrading in place is painful if you have to go like 3 steps and then do the upgrade SS tables along the way and things like that. This helps with that as well, because you have 2 different clusters. You have a lower risk because you don't have to say, okay, well, if something goes sideways, what is my state and how do I unwind from that? It's more like, okay, we have the target and it's completely independent. It's starting from scratch, and you have this origin cluster, and if I ever need to roll back, I'm good. And then you don't even have to do the full cluster. So like you say, I want to separate out this one app that's kind of like a nuisance app or a noisy app. It's really mission critical and we want to keep it on its own hardware. Let's split that one app out. And the ZDM proxy will allow you to do that, or consolidating either direction. When it comes to compatibility, we've tested it against everything you see here in one form or another. I think most of these in production, going from one to the other. It speaks the native protocol versions 2, 3, and 4. And so anything beyond Cassandra 2.1.7, I think, and or similar DataStax Enterprise version, associated DataStax Enterprise version. And it goes to version 4. Version 5, protocol version 5, SQL protocol version 5 is in beta in Cassandra 5, or until Cassandra 5. The ZDM proxy is able to downgrade, kind of like negotiate the protocol down to version 4 if it needs to. So it's not like it's a critical thing that it doesn't have version 5 in there yet. It's just one of those things that we haven't gotten to yet. Cassandra 5's not out yet, but that's one thing that we want to add. So pretty much anything that speaks CQL of any sort should be able to do this. And has this been done before? Yes, we've been doing it for about a little over 2 years. It started development over about 3 years ago. Been doing this for a little over 2 years with a number of customers. We put it into categories of kind of verticals because they oftentimes will have different tolerances for security, for SLAs, for throughputs, and all of that. And so just to give you an idea of, okay, well, has this been done for a lot of clusters? And you have like, lots and lots of clusters for individual companies, or you have like, my favorite is like a gaming company that released a game, like an online massive game with crazy bursty traffic, and they were using the proxy to bifurcate traffic during the production launch. And I'm like, that's a really nice validation that this is not going to fall over.
Yeah.
So.
And also the data volume is like 20 plus terabyte, right? So,
Yeah.
Yeah.
So in the background, you're migrating all the historical data.
Yeah.
And we'll go through some of the so we wanted to kind of give you some context as to why, and then the tools that are involved. So the proxy that I've been talking about, it's a lightweight CQL protocol handler wrapper to be able to do this bifurcation of traffic and keep things in sync. Its one job is to say, I have these 2 clusters. and I need to keep those two clusters in sync after time X. So it handles all the real-time incoming traffic, and at each request, it says, I'm going to synchronously make it so that this cluster and this cluster receive the exact same updates at the exact same consistency level. And it's synchronous. And so, and it's common, it's written in Golang, it's deployed as a Docker container, and it's all open source. And so if you have any issues or whatever, it's an open source project out there. And yeah, so why would we want to have something dedicated for this? And it's stateless. That's the other important thing. It's stateless, so that you're not having to worry about it. It does have to read, to understand whether it's a read or a write to do the appropriate thing. So it does have to kind of, so in terms of end-to-end security, you can have client to proxy encryption, proxy to clusters encryption, but it does need to be able to see what the requests are actually trying to do in terms of reads or writes. And so why would you want to do this? We've seen at other times when people go from one data store to a completely different data store, where they might say, okay, well, let's do this, something with Kafka, something with like, queuing and things like that, or you want to bifurcate within your application. And it puts a lot, it seems like a simple idea in theory, but it puts a lot of burden on the application developers. And if you have hundreds of microservices, you're telling all of those teams with their own kind of requirements, regulatory compliance and all that kind of stuff, that they have to do some throwaway code that has to be tested and all of that, just for this one period of transition. And so this is why we said, let's take this out of the hands of the developers and have this, instead of all these hundreds of people that are working on these applications, put this into the hands of the operators, and so the application developers don't even care. They just say, okay, what do I point my application to? And so that's kind of the rationale here, with the assumption that you're moving from one CQL data store to another CQL data store. The other tool in the toolbox here is the thing that I mentioned at the beginning. It's nice to have something that's kind of a dedicated tool and resource to say, I'm going to migrate and also validate historical data from tables between origin and target clusters. This is an open source tool again. It does things like that you would hope it does, like auto detects the schema. Instead of saying, okay, list all the tables here, list all the tables here, it'll do checking on like UDTs, all the exotic kind of like data types and UDTs, collections, counters. Make sure that the right timestamps and TTLs are preserved from the origin, so you're not stepping on data when you go to the target cluster. It checks for differences, and it even optionally reconciles the data. So if you have some sort of non-idempotent operation, like an lightweight transaction, that depends on the current state of the origin cluster, that's not in the state of currently in the state of the target cluster, you can do this after the fact and say, okay, well, was there anything that is off between these two clusters, and then reconcile that for me to make sure that both clusters are in the same state. And because you're operating within time windows, you can say, okay, up until like beginning of time to time X for when we started using this proxy, only copy that data initially. And then once you've done that, you have that data done. And then as you move forward, you can say, okay, well, you can do incremental reconciliations along the way to say, let's just make sure, that absolutely sure that these two clusters are in sync. I mean, what we've seen is like facility and ease of use and all of that. Those are all great, but consistency of data is what people are very much after. And people don't want to lose their jobs as they migrate from one data store to another. And then obviously you want to be able to tune the reads, for instance, like if you're migrating from one data store to another, the reads on the origin cluster you don't want to interfere with the regular real-time traffic from the origin cluster. So this is all kind of like the tool context. And so,
yeah.
Go ahead, Wayne.
So Jeremy just walked through some of those components. So now we're going to take a closer look at those components that we touch upon, and then we will walk through the migration process in a little bit more detail. Next slide. So before the migration, your application will just do the regular read and write with the CQL driver against your origin cluster, which is to the right, those orange ring as you see here. And next, please. Okay, so this is basically during the migration. So all the activities are happening here. And what basically, as you can see from this picture, we have 2 additional key components into the picture. So that's to avoid introducing any downtime. So one component, as you see in the middle, this ZDM proxy. So those ZDM proxy basically handle the real-time requests generated by the application instance. So the proxy is there to implement the dual write logic so that the same write can be sent concurrently to both the origin and target cluster. And then as you see on the right, the other component that's called the existing data migrator. So it basically transfer all the existing data from the origin to the target. And these 2 components, they are basically independent of each other, but they are used in conjunction to achieve that zero downtime migration. And next, please. So as you see here, we basically set up at least 3 ZDM proxy instances. So they are high throughput and they are stateless, so, which means that they are horizontally scalable. So we configure them to point to both the origin cluster and target cluster with ZDM UTL or Kubernetes. And then we update the application client, as you see on the left. So those clients now point to the proxy. You can actually do a rolling restart of your application servers. So this way, your application can still provide services to the end user without any interruption. And as Jeremy has mentioned previously, the proxy's one job is to keep both clusters in sync per request. And if a write request comes in at a consistency level of the local quorum, it will execute that write at local quorum in parallel on both the origin and target cluster. And also, one other key thing to remember here is that the proxy will only return success to the client if both the origin and target cluster have returned acknowledgement that the write is successful. So as we mentioned earlier, we have an existing data migrator. So the component to the very right. So that's basically migrate historical data from the origin to the target cluster. The existing data migrator can also be served as a validation or reconciliation. And here, through this whole process, as you see in the middle, there's a red arrow that's pointing to the left. That's the read. In here, we are basically just continuing to read from the origin cluster until that whole existing data migrator has finished reading all the data, all the historical data from your origin cluster and move that into the target cluster. So basically, the target cluster has all of the origin cluster's data. And then we can move on to the next stage. OK, so here you can see that we no longer have the existing data migrator because there's no use for that anymore. And also the read arrow to the left is now moved from reading from the origin cluster to the target cluster. So this is where that you're doing the final verification. So you basically you will continue to write to both clusters in case anything goes wrong. That will give you still a chance to roll back. So you can just, if you want to roll back, you just point your application back to the origin cluster. Nothing is lost at all. But I do want to point out that this is the last step before you really cutting completely over to the target cluster. So this is the time that you want to do some final validation of the target cluster's capabilities. By capability, what I mean is that your target cluster, there may be a different CKL store. They need to have exactly what you expect from your application, like in terms of the CKL support and all that stuff, and as well as the capacity. It does have the bandwidth. It's able to process the amount of requests, read and write requests you were expecting from your application. So this is the last stage that you can do that, the final verification. And next, please. So now, after migration, it's actually quite easy. Basically, now you're fully satisfied that the state of the new cluster, so it's able to handle the traffic requirement. We just repoint your application to the target cluster, and the migration is fully done. OK, so next. So yeah, now we kind of like breaking this down into a few high-level phases. just to explain this a little bit more. For phase 0, basically this is the stage that you prepare your target cluster. So this is like, you would need to create the target cluster. You need to configure the access to it. You need to create the schema so that the target cluster schema is matching the origin cluster schema. And then also, very importantly, you want to make sure you test it. You're sure that your target cluster is working well for the application being migrated. And then, you basically just do some validation that this migration is going to work well. This application, once it's pointing to the target, is going to work well. So you are basically, even you don't have any data migrated over yet, you just want to make sure that's happening. Okay, Jeremy, you want to go to phase 1?
So yeah, so that's all the preparatory phase. And then you deploy the ZDM proxy through the Ansible automation or through Kubernetes. And then you point your application servers to the proxy, and then it handles the authentication and the traffic routing to the 2 clusters in each of the areas.
Okay. So at this point, we move on to phase 2. So this is actually, probably the longest running phase in the whole migration, because you are basically talking about doing that existing data migration from the origin to the target. And if you have a very large data footprint, this could take days to finish. This is basically, the whole thing is existing data migrator's job. That's basically, you just let whatever kind of, historical data migration to happen during this time.
Yeah, and people often ask, as we're doing these migrations, how long is this supposed to take? And as long as you want it to take, really. I mean, the data migration is one important element, but as long as you feel comfortable, being on the two clusters with the proxy, is as long as you're wanting to make sure that you don't have any kind of hiccups along the way. This is really meant to be a risk-averse sort of thing, to make sure that you're comfortable with the new cluster and comfortable migrating. And so that leads to number 3 is now that you have a good base of the data sets in both clusters that you think are pretty well good, we've added a feature that's in the middle that says, okay, before I cut read traffic over to the new cluster, I want to make sure, because we've been bifurcating writes this entire time, and your application, when you actually do a cutover, you're going to kind of unleash all of this read traffic over to the new cluster, right? And so we added a step in the middle that says you can optionally do this, but you can point, still the reads go to the origin cluster, but you mirror the reads to the target cluster, and the results are just thrown onto the floor. And the purpose of that is to say, can the target cluster handle gracefully the writes and the reads with sufficient throughput and at those SLAs, at the latencies that you're expecting? So again, this is another step to avoid the risks of surprises as you migrate to the new cluster.
Yeah. So just to add to phase 3, so this optional step is an async dual read. So basically, that means that it's not going to increase your latency. Your read is still going from that primary cluster. So so basically, this is really just to make sure that you introduce extra load on your target, and your target is able to handle that. And now we move on to phase 4. So once the existing data has been fully transferred and any validation check has been successfully executed, target cluster can become your new source of truth for your read. So at this point, you basically flip a switch in the proxy. So then the proxy will basically route all the read to the target cluster. And at the same time, the proxy will still send the writes to both databases so that both databases are kept in sync. And throughout this whole process up to here, as you see at the bottom, we just pointed out that the rollback is still very easy. So if anything goes wrong at any point, you can still just connect your application directly to your origin cluster. And at this point, you don't really have any data loss because it's always dual write. So you don't, if you need, you don't need to do any restore or anything. So it's really it's very low risk kind of, just rollback.
And that gets us to the point of no return, right? So you point your applications directly to the target cluster. Everybody goes home. Everybody's happy. You're saving money, or you've gone to the new place, and things are good. And you still could roll back if you really wanted to. You just do the whole process in reverse. But hopefully, this gated process gives you confidence that this new thing is going to be sufficient for you. And we've had people run on the proxy for a few weeks. We've had people run on the proxy for 6 months. We've had run on the proxy during a go-live event. And so it's not a problem of running on the proxy. It's just a problem of, or it's not a problem, it's just more of a when you feel comfortable. And the whole thing is just to reduce the risk of going from one thing to the other. And so that hopefully gives you a better idea of the high level here. So as we're going forward, I mean, we've tested it in a number of circumstances. We want to do some more testing with Cassandra 5. We want to add version 5 support. We have custom authenticator support for, I think, InstaCluster and Ivan. And that's in a branch right now. We need to do a release with that. Improve the Kubernetes support to have like some more dashboards and things. One thing it does right now is you can configure it to say the now function in CQL, it produces a time UUID, right? And so if you're sending that to 2 clusters and you have 2 different time UUIDs, that's kind of a problem. And so what it does is it says you can optionally have it parse and rewrite that to say, instead of having now, it replaces that now in there with the time UUID. So it's identical to both clusters. We'd like to maybe expand that in the future, improve the parsing and things, because there's a little bit of overhead in there. That's why it's optional. To use like date time CQL functions and UUID functions to replicate that same pattern. But that's stuff that is in our future work. So before we get to questions, we only have a few minutes. These are some of the links. They're all open source projects. The extensive documentation. It was open source a year ago, and we've had a lot of documentation. And Stefano here did a Gitpod interactive scenario. So if you're wondering how this whole process works to try it out, you can go to Gitpod. It creates a cluster for you. You do have to create an Astra account, because Astra is what you're migrating to for the purposes of this kind of enclosed demo, not demo, but walkthrough. So it does all the steps, and you perform the steps, and you can see in the terminals what's going on and the application traffic and all that kind of stuff, and do the rerouting of the stuff. This QR code is to more easily create an Astra account. It's free. It's like no credit card or anything like that. And so this allows you to just kind of go through all those steps, which is kind of the outside of the scope of this conversation. But are there any questions? We have some common questions that we have, but any questions? Yeah, in the middle there? You, yeah. Uh-huh.
What's your architecture to get the data, like exporting and importing? Do you use like CDC, or do you use incremental backups?
Thank you. Yeah, the question is whether or not you use CDC or incremental backups to migrate the data. That's what this handles right here. It's a Spark-based tool that uses CQL to export from the origin. And I mean, there's a number of tools out there, but this one is specifically tailored for CQL workloads to extract and then push to the other data store with the reconciliation and everything.
And sorry, just a quick question.
Sure.
While you're doing the migration, then the import and export functionality that you're using to get the data in, the dual writes would start like after the migration is completed for the existing writes, or does that happen at the same time?
So you can start your historical data migration at any time, even before you even think about putting the proxy in place, because that's going to take some time. And so you don't have to go strictly according to these phases in terms of migrating the data. You can do that previously, and then only do kind of like the migrate and validate of the data with that Cassandra data migrator of the window of time that you haven't already done. So that reduces the time that you have to have the proxy in place. So you could even have the proxy down to a day or two if you wanted to, and done the bulk of the work of migration before that. Is that?
We don't really block it in the sense that customer can start using the proxy even before completing the migration.
Right,
Yeah.
right. And oftentimes people just say, okay, let's start at a time X, and then we'll start the data migration. Oftentimes we've seen it where they do the data migration while the proxy's in place. Yeah, up front with the hat.
Yeah, well, regarding the same, so if the data is being updated along the way, how do you deal with that?
So that's the data migrator will, since Cassandra is kind of like the last write wins, if you take historical data, if this is answering your question, is to say the timestamp of that write is going to be in the past. And if you get new data that comes in, getting the wrap-up signal here. If you get new data that comes in, it'll have a newer timestamp. And so those will reconcile, and then the new data will take precedence over the older data.
Okay. And there were another session about mirroring CQL traffic and shadow Cassandra deployment.
Yeah.
So is that something, I guess this is very similar, right? So
It's very similar. I think this is kind of splitting out applications, and I mean, this is more splitting out applications and other things. It solves similar problems, but it has a different, kind of more of a different use case. That's kind of, yeah. Yeah.
Yeah.
I was just going to say, I'm looking up Piotr, and yeah.
Yeah, those two.
And those guys back there.
Yeah.
But yeah, that's a good question. Yeah. Maybe one more question. And
Yeah.
Yeah, so you talked about that there's no latency during the optional validate reads on the new cluster, but
yeah.
how much latency does the proxy introduce?
That is one of the most common questions that we get, is that it's not free, right? You have something that goes in the middle. Anything you put in the middle is not free. So what we've found through some testing and practical experience is like a couple of milliseconds.
Yeah, so it's a
For each
single digit.
request?
Yeah, single digit millisecond.
Yeah.
Basically the idea is that the
Or
proxy,
each statement, actually.
Yeah, as designed as like a Go, very lightweight Go routine. So it's basically, it doesn't really add too much additional latency, but it's like single digit, like less than 10 or around 10 millisecond, with the proxy in the middle.
Yeah, and that's per statement. So if you have large batches of many statements, the overhead necessarily is the proxy kind of has to go through each statement within the batch and determine if that statement, because you can mix reads and writes, right? So you can have all these statements that you have to kind of say, okay, is this a read or a write? And then I have to send it and that sort of thing. So it's not like it has to do it in serially, but it does have to do the rewrites or the traffic routing of each statement and read each statement. So that's the one caveat, is if you have large batches, then you might want to be careful because the overhead starts to add up. Okay.
Yeah,
I think we're done. If you want to talk to us, we're happy to answer additional questions, but I think we have to wrap up there. Thank you, everyone.
Thank you.
check, 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 check.
Cool. We can go ahead and get started. Happy 4:10 p.m. slot. Y'all are the real troopers getting to the end of the conference, so thank you. My name's Isaac Reith. I lead the NoSQL infrastructure team at Bloomberg. And with me today is Lindsay Saravchak. She's an engineer with me on the NoSQL infrastructure team. It's been almost 7 years since Cassandra as a service came to Bloomberg. Over that time, we've learned a lot about the many obscure ways that Cassandra can break. In this talk, we'll present a few of the problems we've seen over the years, some of the warning signs that Cassandra has for identifying these issues, and what you can do to both fix the issue in the immediate term, as well as prevent it from happening in the future. Before I talk about all of that, I'm going to talk a little bit about Bloomberg, in case you aren't aware of what Bloomberg is and what we do. So Bloomberg is a technology company that provides financial data primarily through software known as the Bloomberg Terminal. The Bloomberg Terminal has more than 350,000 subscribers and offers different financial analytics tools, which we call functions, to finance professionals around the globe who use the data and news we provide to do their jobs every day. We have over 21,000 employees in 70 countries, more than 8,000 of whom are engineers. Our engineers are active members of the open source community, both as users and contributors. If you've merged my PRs, Stefan's in the audience somewhere, thank you. And we even have people who serve as PMC members as well. Bloomberg has transitioned over the last 2 decades to becoming an open source first company. We use hundreds of open source projects to power our products and infrastructure. A little bit about the NoSQL infrastructure team. We offer Cassandra as a managed service to engineers at Bloomberg. Our goal is to make it easy for engineers at Bloomberg to use Cassandra to power their applications without needing to understand the complexities of managing a large-scale distributed database. We started in 2017, and we've been growing ever since. The scale at which we now operate is around 2.5 petabytes of data, served by 3,000 Cassandra nodes, broken into 250 clusters. Operating at this scale has presented a number of interesting challenges, and we'll dive into those next through a bit of a role-playing exercise. Lindsay and I will both take the role of engineers doing an on-call shift for the NoSQL infrastructure team. We'll talk a little bit about the problems we see and how we fix them. But as with all based on real-life media, we'll preface our story with a disclaimer. The events you're about to witness are fictitious and have been condensed into a single on-call shift for dramatization purposes. No engineers were woken up in the middle of the night in the making of this presentation. So I start my on-call shift, and I get my first issue. I log in to figure out what the issue is and assess the impact. I see that disk usage is getting pretty high in a number of our Cassandra nodes. It's not yet impacting our users, but we need to figure out what's going on before the disks fill up. Looking further at some of the Cassandra metrics for the cluster running on these machines, I see that there's a table with a large number of data files in this cluster. When I look at the droppable tombstone ratio, which defines the ratio of data which can be cleaned up by Cassandra to live data, it's very high. So I need to ask myself two questions. One, what is deleting the data and thus generating the tombstones? And two, why isn't compaction deleting the tombstones off of disk? So I take a look at the table schema, and I can see that TTL is very clearly what's generating the tombstones. And the table here is compacting data using time window compaction strategy. On the surface, nothing seems to be too strange here. I then ask myself, why isn't time window compaction strategy cleaning things up? Luckily, Cassandra offers a tool called sstable expired blockers to be able to figure that out. So using that tool, I discover the culprit, and I use the sstable metadata tool to actually inspect the data. One thing that I see on this sstable is that it's mostly expired data. However, the max expiry time, the min expiry time of the data in this sstable is different. And this is what's preventing the data file from being dropped and in turn letting other tombstones build up. So what's actually causing the expiry times to be different? I look at some application code and I see the culprit. There are some code paths which have a using TTL clause, adding to the insert statements. In this case, it's using a TTL of 2 minutes. However, if you remember on the last slide, our default TTL was set to 6 months. So that means that some of our data is expiring in 2 minutes, the other data is expiring at 6 months. And so to explain why this is a problem, I'll go into a small example of how time window compaction strategy works, and we'll be able to illustrate the issue. Well, before we dive into an example, I'll give an overview of time window compaction strategy for those who aren't aware of it. So time window compaction strategy is a compaction strategy whose objective is to create a single data file for a given time window. Data in a given time window will generally be queried together in a time series use case, so having a single data file where all the data for that time window is in the one data file as well as expires at the same time is a really nice optimization we can have. However, once a single sstable is created for a given time window, TWCS won't actually merge it with any other sstables in that time window, and will instead rely on dropping fully expired sstables as well as tombstone compactions to actually clean up the tombstones. So now that we've talked about that, we'll go to an example. So in our very simplistic example, let's say that we have a time window of 1 minute, and we start with no data on disk. So we first start writing some data, and we generate our first sstable, which we call sstable1. In this sstable, what you'll see is some numbers. Those represent partition keys, and those become important in a minute. We continue writing data, and we flush another sstable, sstable2, and then compaction runs and merges them together in an sstable called sstable3. So now 1 minute has passed, and we have like a new time window that started. All the sstables for the old time window have been merged together. We see sstable3. It's actually a pretty nice sstable. All the data in this sstable is expiring within 2 minutes. They all expire at the same time. So we'll keep writing more data, and we'll create a new sstable, sstable4, and sstable5. This is where we start to run into problems. This data is not nearly as nicely organized. Some of the data in each of these sstables expires in 2 minutes, but there is some data that also expires within 6 months. So compaction will run again and merge them together to a new sstable we call sstable6. So now that 2 minutes have passed since the original sstable was created, you'll see that it's fully expired. It would be awesome if we could clean up this data. We don't need it anymore. We know we have a TTL, expiry immutable data type use case. However, recall that Cassandra will no longer run a compaction to merge it with sstable6 because they're part of different time windows. And so instead, we need to rely on purging the fully expired sstable. However, to do that, Cassandra will run a check first to see if there are any partitions which overlap with live data before dropping the sstable. And if it does, that sstable won't actually be dropped. And so what you'll see in this case is, among other partitions, partition 0 and partition 1 overlap between sstable3 and sstable6. Even worse, partition 1 will expire in 6 months, which means sstable3 is going to be sitting around for a while before we're actually able to clean it up. So this is going to be our first issue, and we'll talk about how you can fix this in a minute. But continuing on, we'll flush 2 new sstables, sstable7 and sstable8. which get compacted again into a new systable 9. So now more time has passed since the 2-minute TTL data was written into systable 6, and that's now expired as well. So systable 6 is not fully expired, but it would be really nice if we could run a tombstone compaction to clean things up here. So why isn't Cassandra running that? Well, systable 6 will only have a tombstone compaction run on it if, again, there are no overlaps between other live SS tables. Otherwise, the tombstone compaction by default won't run. So what can we do to actually get Cassandra to clean things up here? Well, the first thing that we can try is by setting the unchecked tombstone compaction parameter in your compaction strategy. This will let Cassandra run a tombstone compaction even if the SS table in question that you want to compact has overlaps with other live SS tables. In this case, only the tombstones which do not overlap will be purged, and this could have helped clean up that data in SS table 6. However, if unchecked tombstone compaction isn't good enough to clean things up, then we can also set allow unsafe aggressive SS table expiration. This name sounds really scary, and I think it's supposed to be kind of scary because it can end up deleting data that you don't want to be deleted if you don't have a 100% append-only TTL use case. So be very careful when setting this argument. You need to set both a JVM option and alter your table's compaction strategy to set it. And this would have allowed us to drop the SS table 3 from our example. So this would help clean things up in the immediate term, but what could we do maybe longer term to fix the problem? Thinking longer term, if you can change your data model to work better with time window compaction strategy by bucketing different expiry times into their own tables, this can help prevent the issue in the first place. But this is only really possible if you know up front all the different TTLs that you need. We understand that sometimes isn't always feasible to do. Sometimes you really do need fully dynamic row-level TTL to solve whatever problem you need to solve. And so in that case, if you can't break apart your TTLs, don't use time window compaction strategy. We'd probably suggest using leveled compaction strategy. It's more aggressive. It'll help purge tombstones more aggressively out of these types of use cases. One thing we're really excited for in Cassandra 5 is unified compaction strategy. So hopefully we can spend a lot less time thinking about compaction. So after getting the tombstone issue out of control, it's a really busy shift for me. I have another problem I got to solve. So all of a sudden, we're starting to see write timeouts occur on a few nodes in one data center. We're not really sure why this is happening, but these writes seem to always be timing out in the same data center. And they're indicating that 3 responses have been received in that data center. And so what this is indicating to us is really that a cross-data center handoff is failing in Cassandra. Looking at the remote data center to where we see these timeouts, we see that one node had an out-of-memory error. But this is really strange, right? Shouldn't the node be down? Like, why is it still getting requests? Why is it still participating in anything? Well, if you use the default JVM option that shipped with Cassandra, there's a flag exit on out-of-memory error that will be set that causes Cassandra to exit when an out-of-memory occurs. However, this flag will only work when an out-of-memory is a result of a heap space or metaspace exhaustion. And for a native thread out-of-memory, the process will sit there still running. So you might then be asking yourself, okay, well, if that process is still running, why is it still reporting us up to the rest of the cluster? And this has to do with gossip. So if the gossip threads are still running, it will still be responding to the pings that the other nodes send to it. And so the cluster will actually think that this node is healthy when it actually can't create any new threads. And so why is this causing a timeout? Well, when a cross-data center coordinator is chosen for the write request will just most of the time be pending, and it won't actually be processed. And because that write request isn't processed, the cross-data center coordinator can't forward on to the replicas in that data center. Then from the query coordinator perspective, you're just going to see a timeout. So what can we do in this situation to make sure that we don't have to deal with this problem? Well, first and foremost, you should identify that a native thread out of memory has occurred. And when this happens, you need to jump into action right away and ensure the node that is killed. There are JVM agents like JVM Quake, which can be really good at helping to automate this problem. But at the very least, you need to make sure the node comes down. So this will help mitigate the issue in the immediate term. But in the longer term, you need to figure out why you're not able to create new threads on a given machine. A lot of the times at Bloomberg, when we've seen this, it's because there's some sort of configuration on the machine that's wrong, like nproc isn't set properly, or maybe you're running with systemd and you forgot to set the task max parameter. And so one thing to note with this is even though that we found this in Cassandra, it's really a problem that plagues all JVM software. So we definitely recommend taking the learnings that we had from this problem and applying them to kind of all your JVM-based applications. So this has been a pretty busy on-call shift for me, and Lindsay can see that I'm getting pretty tired. So she's going to take it over from here, and I'm going to go get some rest.
Enjoy your sleep, Isaac. So I've barely been on call, and I'm already getting paged. Let's see what's happening. All of a sudden, an application is seeing sporadic authorization errors, but we haven't made any updates to the authorization policies for this cluster. On the server side, we see that we're under a lot of load, and we see this specific error message about a failure to authorize a user. What's happening under the hood? So in order to figure that out, we have to see how Cassandra does authentication and authorization. Cassandra maintains internal caches of authorization policies, roles, and credentials on each node. And on a cache hit, the request is authorized. However, if a cache entry has reached its expiry, or if the policy isn't present in the cache, then Cassandra will perform an internal query to system auth roles and role permissions tables in order to refresh it. So why is the failure happening? These authorization queries get added to the queue with other queries, and therefore, when a node is already overloaded, authorization queries can start to time out as well. So if this auth request fails, there really isn't an exception which can be thrown other than unauthorized exception or authentication exception, depending on which part of the pipeline actually fails. And so when this error gets sent back to the client, it gets sent back as an authorization failure, instead of being categorized as a query timeout, which applications will typically retry. So what can we do about this? Well, these types of exceptions will indicate when the exception is a result of a failure to authenticate or authorize, including when these system auth table queries time out. So we can know that these failures should be retried. So we highly recommend adding retries and error handling to your application for this case if you haven't already. Now, this error isn't always intuitive, so the error message itself is going to have details around the failure so that you know you're hitting this case. And if you're curious about this and you want to understand it more thoroughly, Cassandra 15041 has more information. In maybe a medium-term solution, increasing the validity of the caches with configs such as roles validity in milliseconds, permissions validity in milliseconds, and credentials validity in milliseconds is going to result in fewer cache refreshes, which can further help reduce these failures. And in more of a long-term solution, if you're not on Cassandra 4.1, you want to upgrade so you can use this last feature, configure Cassandra to asynchronously refresh this cache with your roles cache active update, permissions cache active update, and credentials cache active update. But you guys should have these slides so you can see this later. To emphasize how these last two solutions can help, let's revisit this diagram. So when we set the async refresh, these additional system auth queries aren't going to happen at query time. And while the validity and the refresh configs actually both default to the same value of 2 seconds, a strategy could be to set the async refresh period to a value that's less than the cache validity, so you know you always hit the cache. And also, if you were at Mick's talk earlier, I believe he said you could up it to like 30 seconds, so there's that too. It's also worth noting that while using async refresh will help avoid this type of error, it doesn't necessarily reduce load on your cluster. So in times of high load, you may still experience the load shedding that causes this problem, and the queries to system auth tables can still time out, but the difference is that this error isn't going to get sent back to the client and cause this confusion. And additionally, you may now be reading from these tables more frequently, depending on the refresh rate that you set, so be conscious about this as well. We get yet another call. It looks like some nodes are under higher load than others, which is causing timeouts. Let's see what's happening. In addition to seeing timeouts, we're also getting alerts that the disk is filling up on some of these nodes within the cluster, and we look at node tool status to help us understand a bit more about the topology. We see that this cluster is very imbalanced. There are some nodes which are going to be like twice the size of others, right? What is causing this? So to figure that out, we need to look at how Cassandra handles data distribution. Cassandra distributes data around the cluster and determines which nodes own what data when nodes are initially added to the cluster. So assume these 6 nodes are in one data center here. This makes up what's called the token ring. Each node is responsible for a subset of data determined by this ring. The partition key, which is defined in your data model, is hashed to determine the first replica where the data is stored. So for example, in the query we see here, the partition key is the name John Doe. The value is hashed to equal the token 7. Now, Cassandra uses consistent hashing, so no matter how many nodes we add to this cluster, the partition key is always going to hash to the same token value. We see that node 1 is the node responsible for this data because it owns tokens 0 through 10. If we assume that we have a replication factor of 3, we have 2 more replicas that are going to hold this data. Now, the replicas are determined by moving clockwise around the ring and selecting the first node that's in a different rack than previously chosen replicas until the replication factor is met. So we see in this example, we now have node 2, which is on rack 2, and node 4, which is on rack 3, have been selected as replicas. Now imagine there's a rack with only one machine. This one node is going to be supporting data that other racks would split between several nodes. So this is going to become a problem. The issue is even clearer when we see the physical view here. Rack 1 has only one node in it and no more inventory to add into the cluster. So we'll need to get rack 1 out of the cluster entirely and add in a few more nodes from a new rack, such as rack 0 here, which has more inventory. Now, in this cluster example, we have 4 racks of nodes to choose from, but a replication factor of 3. So how can the relationship between replication factor and rack count help us to prevent this in the future? So having a replication factor that's less than the rack count is going to make it more difficult to tell which nodes are replicas for what data, as Cassandra can choose many combinations of racks depending on the token value of the partition key and the token ownership of the nodes in the cluster, as we saw before. So one partition might be replicated across nodes in racks 1, 2, and 3, but another partition may be on nodes of racks 1, 3, and 4. So this is going to result in some imbalance, and some racks may end up being responsible for more data than others, depending on the partition strategy. Because remember, the partition hash determines where we start in the ring. On the flip side, having a replication factor greater than the rack count will result in placing replicas within the same rack, which Cassandra tries to avoid. This makes your cluster more susceptible to outages, as nodes within the same rack could all come down at the same time due to network or cooling issues, and that's going to result in loss of quorum, which obviously we don't want. So the solution here is to set the number of racks equal to your replication factor by creating a logical grouping of machines. This results in Cassandra placing a replica in each rack and spreading data between the racks. So let's visualize this. We see here now with a replication factor of 3 and a rack count of 3, we know that there's a replica in each rack, and the machines within the rack split the ownership of all the data. And since all machines are now part of one of 3 racks, the same set of machines now results in more usable inventory available for the cluster. Now, even though we're no longer bound by the physical location of the machine when adding machines into the cluster, it's still important to remember the physical locations when creating these logical groups, right? When taking this approach, you should ensure that the machines on the same physical rack are part of the same replication group so that no 2 replicas are placed on the same physical rack. And if you're in AWS using the EC2 snitch or the EC2 multi-region snitch, it's important to align the number of availability zones that you deploy in with the replication factor, since these snitches are going to use the availability zone as rack information. So now when all the nodes in the cluster begin to fill up, we can spread the data out more easily by adding more nodes in each rack. It's important to note that this strategy really only works when you enable the config allocate tokens for key space or allocate tokens for replication factor, depending on which Cassandra version you're running. These configs trigger the distribution of tokens more evenly around the cluster, taking into account your replication factor here. So while the strategy as a whole is going to help you with controlling data distribution around your cluster, it's not going to solve large partitions. It's not going to solve the imbalance of data relating to a bad partition strategy, so still be conscious about that. This is not an out. We made it to the end of our own cost lift. So what did we learn? In addition to the solutions of the individual problems that we saw, there are some themes across all of these problems that we need to take note of going forward. First, observability is immensely helpful in identifying issues in Cassandra. There are a lot of metrics available, as well as very thorough logging. So make sure to use these in understanding what's going wrong here. In addition to metrics and logs, Cassandra offers great tools such as Node Tool, SS Table metadata, and SS Table expired blockers that help diagnose these cluster issues. Second, configuration is very important. It's really tempting to use the default configs, but there are a lot of opportunities to enhance performance and prevent the types of issues that we talked about, if you're willing to dig a bit deeper. In addition to the official documentation, the ASF JIRA is also very helpful in understanding what these configurations do and documents some of the more esoteric configurations that Cassandra offers. And finally, I cannot stress this enough, be proactive when monitoring your systems. Learn the early warning signs, such as an increasing droppable tombstone ratio, and act when you see them to prevent the fall of your application. Okay, so we're gonna take questions, but while we do that, we're hiring. So if anything that we said today sounds interesting, I promise that's not a typical on-call shift. Come talk to us. Feel free to scan the QR code. So that's it.
Any questions?
Oh, you're gonna let us off easy?
Nice. We'll take it. I'm gonna talk about that?
Yeah.
I'd say in like the extreme, so that's like a very real example that we had where we had a single like rack node and a single rack like that. Those examples, it didn't really help a whole lot, and we did need to be able to add inventory in there to spread out the load. Before we went with the strategy of just racks equals replication factor, just setting that parameter did help a lot with rebalancing your data. But for an example like that, you still need to be able to spread out that load a little bit more. Yeah. All right, well, if there's no other questions, I mean, we'll be right over here, so you can come ask us questions, or you know where to find us. Thank you all for making it this far into the conference. Really appreciate you all coming to the talk, and hope you enjoy the rest of your day.
Acum chestii. Oricum. Nu-i pasă nimănui câțiva oameni. Și-au făcut și date-urile. Trebuie să începem câteva.
Shall we begin? Hello, I'm Stefan, software developer at Adobe, and along with my colleague Sherban, today we're going to share a few things about Adobe Audience Manager, what role Cassandra plays, and some stories on how we turned our Cassandra setup into something more efficient and easier to maintain. First, a few words about Adobe Audience Manager. Adobe Audience Manager is part of Adobe Experience Cloud, a business-to-business range of products and services used for managing the entire customer experience. Audience Manager is a data management platform service. Its main goal is to answer the question, who is this user? To achieve this, billions of data points are collected, classified, and organized. The operation scale of this service is really big. I'll present some numbers shortly. In order to minimize client request latency, data is collected through 8 geographically distributed edge data centers, as shown here. All the data collected through these centers is then pushed to a core database, a setup of HBase running in a single central location. Afterwards, the most recently used data is pushed back to the edge locations so that each location stores a persistent cache of the entire core data. And this is where you use Cassandra for. Some numbers here. We've got a peak number of daily client requests in Audience Manager of 51 billion. That translates to roughly 313 billion of daily Cassandra requests. As already mentioned, we are deployed in 8 AWS regions. We are running 34 Cassandra clusters on more than 800 instances, holding 260 terabytes of data. Now that you have an image on who we are, let me tell you what subjects we are going to discuss in this presentation. First, our architecture and its particularities. Then, split brain, dividing an edge location without downtime. Event-driven automation, a process that we have successfully implemented. And token awareness, a Cassandra feature that really challenged us. So, we go on with the architecture. We'll go from the core database, as previously mentioned, an edge-based setup in a single central location. Its main purpose is to store persistently all the data that we collect, and also it is used for batch processing. Data here arrives from the data collection service, we'll talk about it, but also from other flows. The profile cache service, how we officially call the Cassandra setup, is the caching system that is present in all the 8 edge regions. It has 2 types of clusters in terms of usage patterns, and on the other hand, it has other two types of clusters in terms of data access management, backend and real-time. We'll elaborate this. The data collection service is the Java application that serves the client requests, interacting with Cassandra, and also pushing data to the core database. It only writes data in the real-time clusters but it reads it from both the backend and real-time clusters, and merging the result before sending a final response. And I'll tell you why. But now back to our main focus, the Cassandra setup. There are 4 main Cassandra clusters in each of the edge regions, along with 2 special clusters only in the US regions that serve for a different purpose. So in total, we are managing 34 Cassandra clusters. Our smallest setup has 4 nodes, while our biggest one ever was scaled to 148 nodes. Regarding the profile and ID mapping clusters, they have different schemas and have been separated due to a difference in the ratio of reads to writes, which means that they need to be scaled separately. So it was more efficient to split them apart. In terms of data access, we have the real-time clusters that support read and write operations from the data collection service. They contain new, fresh data, and that is only present in that particular edge region until around 24 hours later, when it is pushed from the backend from the core database to the backend clusters in 1 or more regions. The backend clusters are read-only. New data only arrives through bulk loading from the core database. And the thing is that the data collection service, when serving a read request, reads data from both the backend cluster, where it is historically aggregated and usually more complex, and from the real-time cluster, where it is recent, merging the response before sending it. An interesting feature of our setup is the replication factor of 2 that leads to a consistency level of 1 for both reads and writes. This basically means endangering the consistency. We only wait for one of the nodes that hold the data for a request to return the fastest one, as shown in the illustration that I prepared. So we have a DCS request that reaches a coordinator node. It is forwarded to the replicas that hold that particular data. The coordinator waits for only one response before forwarding it to the DCS, the other response being dismissed. Why are we OK with this? First of all, because it's cost effective. For storing data, we only use 2/3 of the infrastructure required for a replication factor of 3, because obviously we are storing 1/3 less data. But we also assume that we provide a better latency, because we only wait for the fastest replica to respond, not for the fastest 2 replicas to respond. Then, regarding consistency, we are well covered by our bulk loading mechanism. All the data reaches eventually after most 24 hours the backend clusters, which are read-only, and due to this characteristic, they always contain the same data on the main and the replica location. So no matter which one of them is the fastest to respond, the response is always the same. So inconsistencies might only appear in real-time clusters with fresh data, but are, however, seldom due to network issues or crash nodes that have faulty hint mechanisms. But in these cases, we are covered by our SLAs because we still provide data accurate enough. And let me illustrate this. Let's say that we have a write request to the real-time cluster for profile 1 with color red that reaches both of the replica locations. Then we have a write request for profile 1 with color green that only reaches one of the replica location. And then a read request for profile 1. It reaches the outdated replica in the real-time cluster and the backend cluster. When we get the responses, the data in the backend cluster is more complex, while the data in the real-time cluster is not the most up-to-date. So we merge the result, send it to the DCS, and then to the client. And the idea is that we provide not the most up-to-date data, but we provide an updated data relative to what we have in the backend cluster. And this is considered correct enough. But anyways, this happens rarely.
So now about how we trigger the split brain situation. For business-related reasons, we needed to add a new edge data center in India. It was intended to take over part of the traffic that was going to the Singapore region without any noticeable disruption. There were several other issues in doing this migration. I will only go through the Cassandra stuff. The goal was to replicate the APSI cluster in the India data center and keep them synchronized during the transition. Since this was triggered through a DNS change, it wasn't going to be instantaneous. So we needed to keep the cluster synchronized during the entire period. There were two very different problems, synchronizing the real-time clusters and the backend ones. Since the backend clusters are read-only as seen from the Java application, it was much easier to do that there and much more challenging on the real-time clusters. So for the real-time, we had several options. First, it was possible to duplicate the incoming HTTP traffic from the APSE instances and send it to India using tools such as GoReplay. We are already using that for samples of traffic. Then the DCS servers from India would write the data to their Cassandra clusters. The main risk here was that this would also duplicate several business application data flows, sending the same data twice, once from APSI, once from India. It was possible to prevent it, but it would be very, very difficult to manage this during the DNS transition, and we would end up with duplicated data. Also, a serious risk of network or GoReplay errors with no recovery mechanism in case of losing large amounts of data. So this was only a very theoretical option, very quick to dismiss. Instead of duplicating the HTTP traffic, we could have duplicated the SQL writes. We already had support in the application for writing to multiple Cassandra clusters, and with VPC peering, the India cluster would have been accessed from the APSE Java application without any problem. This would have solved the business data duplication issue, but we would still have network latency problems and no retry mechanism. Our application is built for a P95 Cassandra latency SLT of 10 milliseconds. So it was something that we were not provisioned for. There was a serious risk of not getting the data due to timeouts, considering this SLT. And or on the other way, of impacting the DCS performance in the APSE clusters due to waiting for an answer. I should add here, there was an earlier data stacks presentation today about using a TCP reverse proxy to duplicate the SQL traffic. We didn't do that, we did that at the application level, but it has been a very, very useful tool for us, allowing us to test lots of changes on the production traffic. Another option was to use Cassandra multi-data center replication. This will solve the network and latency issues since the writes will go only to the APSE region and allow Cassandra to take care of the synchronization. The main drawback here was the potential impact on changing the APSE production clusters. Also, lack of experience since we never used this before. And then we had no idea about how to split a multi-data center cluster into two regions. So the last option is a combination of the second and the third. The idea was to create a duplicate cluster in APSI with the same mechanism, with writing to multiple clusters, and then have a multi-data center replication between it and the new cluster in India. This way, the APSI production cluster would not be touched, so there was no danger there. And there was no need to do the split required by the third option. We would just drop the UPSI cluster. And on first look, this was great. We decided to try it. And we'll see why it didn't work. The first problem that we had was the Cassandra snitch. According to the documentation available then, the EC2 snitch that we used was supposed to run only for single region deployments, and multi-region deployments required Cassandra instances to use EC2 multi-region snitch and rely on public IP. But I also knew that AWS had somewhat recently added intra-region VPC peering, so it could have been possible to use only private IPs in a multi-data center cluster. The EC2 multi-region snitch was probably done before this was available. So I decided to look into the source code of the snitches. The EC2 multi-region snitch inherits the single region snitch, and it only does what is in this slide. It's not a lot. There is important point here is that there is no rack data center logic, so that is probably done in EC2 snitch. And it's only doing two additional things. It's using public IP for broadcast and sends gossip traffic on both public and private IPs. That's all that it's doing. So that meant that EC2 snitch has multi-data center support, it's just not using it. There was no reason why this would not work with VPC peering. And so this was worth testing. This would prevent a snitch change, not to mention the public IP issue, which we were running only with private IPs. And in the end, it did work, and I made a small open source contribution to update the documentation to reflect the AWS VPC peering. So this was the plan. First, create a secondary cluster in UPSI, set DCS, the Java application, to read-write to this cluster, but not use the reads. Set up VPC peering, add India data center using the documentation provided by DataStax, connect India to its Cassandra clusters, do the DNS changes, and after these are propagated, destroy the UPSI secondary cluster using the documented procedure. And thus we would have a single region India cluster, which was the original goal. There were some prerequisites to apply this. First, use local one instead of one, so that the nodes used are in the local data center. Second, use DC-aware round-robin policy instead of round-robin policy. Otherwise, a remote coordinator will be chosen, creating latency issues. And we actually missed this initially, and well, we'll see later. And put network topology strategy on system key spaces, which is something that actually was an earlier presentation advising to do this anyway. To bootstrap, we start by creating EC2 instances in the new data centers with seeds in both without starting Cassandra on them. Then add these new added India seeds in UPSI instances and do a rolling restart. Start Cassandra on each node in India, first on seeds and then on the rest, alternating between AZs. At this point, these nodes have no data, and further, they don't see themselves as having any data ownership. And this is basically this is the procedure documented by DataStax, but it's something that is not usually done a lot, so that's why I'm going through this. To change the ownership issue, an alter key space is required, declaring a new data center and its replication factor. And this will not trigger a data transfer. For that, node tool rebuild is required. So data will start to be streamed from OPSI, just like on adding or decommissioning, with the difference that this can be run in parallel and to monitor node tool net stats is okay. Several unforeseen problems. The easiest was there were actually 3 system key spaces, not 2. More serious was a very high number of timeouts on the OPSI cluster, 375,000 versus 57 on a normal production cluster. It started when the OPSI servers were restarted with the new India seeds added, and stopped very abruptly when the new data center was added with the alter key space. And this was, as mentioned earlier, this was due to not using the DC-aware round-robin policy. So sometimes these new India instances were being selected as coordinators, triggering this latency and timeouts. When we moved to DC-aware round-robin policy, the timeouts were normal, and it was barely possible to see any change when we did the procedure. Another problem was the very, very poor token distribution. We are using the token allocation algorithm. And in India, we had one node with 70% of the total data load and another with 0.7%. And it's quite normal if you think about it, since there is no data for the token allocation algorithm in that region to run on it when Cassandra is started and the token ranges are allocated. To solve it, we redid this, added only the 2 seeds and run node tool rebuild on them to get all the data on the seeds, and then add the rest of the nodes in the regular way so the algorithm could run. And obviously this required larger instances and would not work on larger data sets. Another option would be to copy in that situation would be to copy the token distribution from OPSI and set it with the initial token setting. But the most serious problem was the cluster name setting. It must be the same in the 2 data center, and as this comment indicates, this is preventing servers from joining the wrong cluster, which actually happened to us. At some point, I put the wrong IPs in the configuration files, thus mixing the clusters, and this actually prevented the instances being added to the wrong cluster. But this was very nice, but it also meant that the plan was not viable since we could not have the same cluster name as in the rest of the regions. Of course, it was possible to actually accept this and have different cluster names, but it was very quickly obvious that it will create lots of soft issues in other places, in configuration, in observability, in automation. This was something that we wanted to avoid, and we were sure that it will generate a lot of problems and errors. It might have been possible to change the name to the normal one later, but this was not documented. It required maybe a rolling restart. There was no sure thing that it will work, and there was no fallback in case something went wrong. Another option would be to go back to our original variants, to use option 3 to replicate between production clusters. This would avoid any naming issues, and by then we started to have some experience with playing with multi-data center clusters. And it was easy to test using the duplicated clusters. So we decided to try it. I'll go now to the plan that we implemented to split the clusters. There were plenty of tests, intermediate tests that I'll not go through. This is based on the documentation for decommissioning a data center with some very significant changes. Of course, we need to monitor timeouts, response time, read-write counts, and we did that when we tested. The first step was to cut the network between the data centers. That was very easy to do with AWS subnet change. So from now on, each cluster would see the other one as being down. And all operations will have to be done in each data center since they will not propagate to the other. So I was tricking each one of them to see that the remote cluster is being decommissioned. On a seed in each region, run this alter key space to remove the other data center. So the reverse of what we were doing earlier. There was an expected warning message that schema cannot be propagated. That was normal due to the network. And now when we are running describe cluster, it will show the remote IPs as unreachable and with unknown schema. And then all that we had to do was to remove each remote node one at a time using node to assassinate from the local data center. So in APSE, I would run node to assassinate and give the IDs of the nodes in India and the other way around. And when all of them are being removed, node to describe cluster will no longer show the unreachable nodes and will no longer show a multi-data center cluster. And all that is left to be done is to remove the remote seeds from the configuration file and do a rolling restart. For fun, we did some testing with, we restored the network connection, we restarted the node and checked that it's not joining the remote cluster and they are completely separated. And this was the intentional split brain that gave the title of this. These were the timeouts during testing, basically no impact of the change. When we did in production, there were some significant timeouts, but still they only briefly reached 1% of the total traffic. That was well within SLA, especially since it wasn't a sustained timeout. On the back end, it was much easier due to previous experiences. First, created new empty Cassandra cluster in India region, create AWS resources for the Hadoop data push, that is SQS and S3, and specialized instances that are doing the data push. Then duplicate all notifications for APSE queues in additional queues for India. And so India will process two times as many queues. And after this is working for at least 1 day, so we started to see data clusters filling in with data. Take a snapshot from APSE region, copy it to India, and then restore it there through streaming. Actually, copy only half of the snapshot from one AZ since there was no need to duplicate the data. We were using 2 AZs. And in the same time, keep streaming from Hadoop. There will be duplicates in doing that, but Cassandra will handle the duplication. There will be a lot of compactions in doing this restore with streaming, but that's okay since the cluster is not yet used and it was easy to configure it for maximum compaction performance. And then run a Python script that take samples from each cluster and compare them. There were several problems also here, but nothing serious. Things like instance availability, since India was back then a new region, or problems with AWS SDK versions. They were too old, they didn't have the India endpoints. But again, nothing serious. And after the DNS transition is complete, stop sending the APSI data, and that meant that's for both real-time and backend. The cluster will contain APSI-specific data, which will disappear in time due to TTL. That's also true in the other region.
Now let's discuss about event-driven automation. A common situation on Cassandra is when a node crashes due to an AWS hardware issue. And the data cannot be recovered in our case because we are using ephemeral storage for cost efficiency reasons. For us, this means node replacement, and we do it as fast as we can. But many of these problems are detected by AWS prior to their happening, when they are expected to happen, and signaled through health events. AWS also provides a self-healing mechanism for this, but this mechanism is only triggered in 2 weeks' time and still involves data loss because it doesn't perform Cassandra node replacement. So our goal is to prevent the nodes crashing by being proactive and replacing the nodes after receiving the health event and such, doing it in a moment of time that the situation allows us to. So because we react to an event, we call this process to be event-driven. And the thing is that for such problems, in order to eliminate the engineer's intervention, there are tools such as the one that we used, Stackstorm, an event-driven automation system that we have deployed from the beginning in Kubernetes, which was very effective. And for this, I provided data from the last month when out of the 19 total node replacements, 13 were performed by Stackstorm, or better said, 70% of them. But I brought the statistics for the entire last year, and monthly, between 50 and 90% of the node replacements have been automatically performed through Stackstorm. So what architecture we used? We basically redirected the health events as notifications to queues in AWS, and we only used one Stackstorm sensor to poll each of the queues in different AWS accounts, different regions, and triggering a workflow for replacing the node. This workflow performs the exact same actions as an engineer would have done, like stopping and starting the instance, running an Ansible playbook for the Cassandra replacement. Most important here is that this workflow is only triggered when the situation is okay, so that it does not cause an incident. And for this reason, it checks that no neighboring node is down. So no other node that shares data with the one to be replaced is down. And look, here is all we are aware about when Stackstorm does its job. A Slack message when it begins, and a Slack message when it finishes.
And, the last topic, short story about how we didn't actually use token-aware load balancing despite setting it. There will not be many details here about load balancing policies. I'm sure that it's known. It's a setting on the Cassandra driver which determines which nodes will be used as coordinators. Token-aware will attempt to send requests to the node that owns the data. Our policy setting is latency-aware over token-aware, but it didn't really work without us realizing it. This is an example of latency-aware behavior. On a separate occasion, I ran a test to change the JVM and garbage collection on one node. That increased its latency, and then it started to receive only about 80% of the traffic of the others. For token-aware, there are a few requirements. It needs to know somehow what's the partition key for a given query in order to find the servers where that data is. It does this in the getRoutingKey method. If it cannot determine the partition key, it will return null, and the load balancing will fall back to the next policy. There is no warning here, and that's what created issues for us. That was what was happening. The problem was that we were using a blob field for the partition key converted from string. The conversion was done with a text as blob Cassandra function, which was evaluated on the Cassandra coordinator. So there was no way for the driver to determine the value of the primary key in the Java application. And the getRoutingKey was always returning null. So always it was going directly to the latency aware. And fixing this was very simple. Stop using this function and convert the value in our Java code with byte buffer util wrap function in all statements. Here is an insert statement, select one, and the usage of the wrap function. Very simple and very effective. There was an immediate improvement in latency. We did see some hotspots on some small clusters, but it was still worth doing it. Actually, in most cases, those hotspots actually indicated a pre-existing issue that needed to be addressed anyway. That's all. Thank you.
We'll take questions on the hallway or something, because we know it's the last presentation and it was quite long. So thank you again. Tu nu știi ce s-a întâmplat. Tu n-ai fost atent. Îți făcea omul ăla cu mâna.